Two red dots appeared at the edge of everything, faint, distant, almost invisible against the black. But they passed every test. The spectrum said early universe, the brightness said primordial, the color said hydrogen from the cosmic dawn, light that left its source 200 million years after the Big Bang. For a brief, dizzying moment, astronomers believed they were looking at the oldest galaxies ever recorded. Objects that formed before stars had time to forge heavy elements, before spiral arms and supermassive black holes, before galaxies learned how to behave. The James Webb Space Telescope had done what it was built to do. It had reached back to the beginning, and then the dots moved, not away, not toward us, across the sky. A slow, patient drift that no object 13 billion light-years away has any right to perform. Proper motion. The kind of movement you only see in something close, something local, something that has been sitting in our galactic neighborhood the entire time, wearing a perfect disguise. What followed was not a correction. It was a revelation, because the light signature of hydrogen at the dawn of time and the light signature of methane in a failed star drifting through the Milky Way are functionally identical. Two completely different objects, two completely different eras, one infrared fingerprint, and suddenly the edge of the universe was gone. What remained were brown dwarfs, ancient, cold, older than our sun, wandering silently through our own galaxy like impostors no one thought to question. This is the story of how the oldest thing we thought we found turned out to be closer than we ever imagined. How distance became deception, and how sometimes the most profound discoveries are not out there at the border of time, but right here, hiding in plain sight. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Chapter 1. The Cosmic Mirage. Two red dots at the edge of time. The James Webb Space Telescope launched on Christmas Day, 2021, and everything changed. Not immediately, not all at once, but quietly, systematically, the way a foundation shifts before the walls start to crack. Webb was built to see what Hubble could not, to push past the visible spectrum into the deep infrared, where the most ancient light in the universe finally arrives after billions of years of travel. Light so old that by the time it reaches us, it has been stretched by the expansion of space itself into wavelengths our eyes cannot detect. Webb was designed to catch that light, to decode it, to tell us what the universe looked like when it was still learning how to build galaxies. Hubble had done extraordinary work for 3 decades. It gave us the deep field images, those tiny patches of seemingly empty sky that turned out to be packed with thousands of galaxies stretching back across cosmic time. It showed us the universe at 1 billion years old, then 500 million, pushing closer and closer to the beginning. But Hubble had limits. Its mirror was too small. Its instruments were tuned to wavelengths that could not reach far enough. By the time you get back to the first few 100 million years after the Big Bang, the light has redshifted so dramatically that Hubble simply goes blind. It is like trying to listen to a conversation happening on the other side of a mountain. You know someone is talking, you just cannot hear the words. Webb was built with a mirror more than 6 meters across, coated in a thin layer of gold to maximize infrared reflection. It carries 4 main instruments, each one calibrated to detect light at wavelengths Hubble could barely touch. And it orbits the Sun at a point called Lagrange 2, about 1.5 million kilometers from Earth, where the combined gravity of the Earth and Sun holds it in a stable position, far from the heat and light pollution of our planet. Out there, In the cold and the dark, Webb can stare at a single patch of sky for hundreds of hours without blinking, collecting photons one by one from objects so distant and so faint that their combined light would not be enough to illuminate a single grain of sand. The first science images came back in July 2022, and the astronomy community held its breath. Webb's first deep field showed galaxies at distances Hubble had struggled to reach, and it did so with a clarity that made grown scientists cry in press conferences. Within weeks, teams around the world were publishing papers on what Webb had found: early galaxies, lots of them, brighter than expected, larger than expected, more structured than expected. The standard model of cosmology, the lambda cold dark matter framework that had guided the field for decades, suddenly looked like it might have a problem. Then came the red dots. The bullet cluster is one of the most famous objects in observational cosmology. It is not a single object, really. It is two galaxy clusters that collided with each other about 150 million years ago, passing through one another at speeds of several million kilometers per hour. The collision separated the cluster's visible matter, mostly stars and hot gas, from their dark matter halos. We know this because the visible gas, which emits X-rays, ended up in one place, while the gravitational lensing, which traces the mass and therefore the dark matter, ended up somewhere else. The bullet cluster became one of the strongest pieces of evidence that dark matter is real, that it exists as something distinct from ordinary matter, and that it behaves exactly the way the theory predicts. But the bullet cluster is also a gravitational lens, a powerful one. The combined mass of those two colliding clusters warps the space around them so severely that light from galaxies far behind them gets bent, magnified, and sometimes split into multiple images. Astronomers call this gravitational lensing, and it is one of the most useful tools in modern cosmology. Point a telescope at a massive lensing cluster and you get a free magnifying glass, boosting the light from faint background galaxies that would otherwise be invisible. The bullet cluster, because of its size and its clean geometry, is one of the best natural lenses in the sky. So when Webb needed a target for deep observations of the early universe, the bullet cluster made the list. In early 2023, a research team pointed Webb's near-infrared camera, NIR-CAM, at the bullet cluster field and began a long integration, hours of exposure time, stacking image after image to pull signal out of noise. When the data came back and the team started processing it, they found what they were looking for: faint arcs and smudges scattered across the field, each one a distant galaxy magnified by the cluster's gravity. Standard procedure, expected results. And then, sitting quietly in the data, two red dots. They were faint, barely there, point-like sources, meaning they did not show any obvious structure or extension, just tiny red pinpricks against the black. In any other context, they would have been ignored, filed away as noise or instrumental artifacts, but these dots were red in a very specific way. Their light was almost entirely absent at shorter wavelengths, the blues and greens, and it peaked sharply in the deep infrared. That spectral signature, that particular way of being red, is not random. It is the signature of extreme distance. When the universe expands, it stretches the light traveling through it. A photon that leaves a galaxy as ultraviolet radiation, the kind emitted by hot young stars, gets pulled and stretched over billions of years until by the time it arrives at Earth, it has become infrared. The amount of stretching tells you how far the light has traveled, and therefore how far back in time you are looking. Astronomers measure this stretching with a number called redshift. A redshift of 0 means the object is sitting right next to you, not moving. A redshift of 1 means the light has been stretched to twice its original wavelength. A redshift of 10 means the universe has expanded so much since the light was emitted that the wavelength is now 11 times longer. Hubble, at its best, could reliably measure galaxies out to a redshift of about 11, which corresponds to roughly 400 million years after the Big Bang. The 2 red dots in the bullet cluster field had spectral profiles consistent with redshifts significantly higher than that. Initial estimates, based on their colors alone, placed them somewhere between redshift 12 and redshift 17. If those numbers held up, if the objects were really that distant, then the light reaching Webb's detectors had been traveling for more than 13.5 billion years. The universe, when that light was emitted, would have been somewhere between 200 and 300 million years old, barely out of the cosmic dark ages. A time when the first stars were supposed to still be struggling to ignite, when galaxies were supposed to be small, dim, chaotic clumps of gas. A time, in other words, when nothing like a mature galaxy should exist. And yet there they were, 2 faint red dots, sitting exactly where the math said the earliest objects in the universe should be. The excitement was immediate. Within weeks, word started spreading through the astronomy community. Conference talks were rescheduled, preprint servers filled up with papers analyzing the data. Some researchers called them candidate galaxies. Others were more cautious, calling them sources or objects, refusing to commit to a classification until more data came in. But the possibility, the tantalizing, universe-rewriting possibility, was that Webb had found the most distant galaxies ever observed, relics from the very edge of cosmic time, sitting just a few 100 million years downstream from the Big Bang itself. Rachel Somerville, an astrophysicist who had spent her career modeling how galaxies form, later said there was a lot of press around the idea that these discoveries were a challenge to the basic paradigm of cosmology. That phrasing, a lot of press, is scientist speak for the story got out of control, and it did. Headlines started appearing in major outlets. Phrases like impossible galaxies and universe breakers showed up in articles written for general audiences. The narrative was clean and irresistible. The most powerful telescope humanity had ever built had looked deeper into the past than anyone thought possible, and it had found something that should not be there. The standard model, the framework that had explained everything from the cosmic microwave background to the distribution of galaxies across billions of light years, suddenly looked like it might be wrong. Not everyone bought it. Caution is baked into the scientific process, especially in a field as precise and as competitive as cosmology. The 2 red dots were candidates, not confirmations. Candidate in astronomy means we think we know what this is, but we have not finished checking. The initial identification was based on photometry, which is a fancy way of saying the team measured how bright the objects were in different filters and used those measurements to estimate their distances. Photometry is fast, it is efficient. It lets you screen hundreds of objects in a single image and flag the interesting ones for follow-up. But it is not definitive. Colors can lie. A very distant galaxy and a much closer object with unusual dust or chemistry can sometimes produce similar spectral profiles. To know for sure, you need spectroscopy. You need to split the light into its component wavelengths and look for the sharp, unmistakable lines produced by hydrogen, oxygen, carbon, and the other elements that leave fingerprints in a galaxy's spectrum. The problem was that spectroscopy takes time, a lot of time. NIRCam, the instrument that took the initial images, is a camera. It is built for wide-field surveys, for mapping large areas of sky and finding targets. NIRSpec, Webb's spectrograph, is built for detailed follow-up. It stares at individual objects, collects their light for hours, and produces the kind of high-resolution data that can confirm or rule out a distance estimate. But telescope time is precious. Webb is the most oversubscribed observatory in history. Every hour of observation has been fought over, debated, prioritized by committees. Getting follow-up spectroscopy on 2 faint red dots, no matter how exciting the initial photometry looked, was not automatic. It would take months, maybe longer, so the field waited. And while it waited, people talked. Some researchers started running simulations, asking whether the standard model could produce galaxies this bright this early if you tweaked the parameters just right. Could the first stars have formed faster than expected? Could early black holes have injected enough energy into their surroundings to accelerate star formation? Could the usual assumptions about how gas cools and collapses in the early universe be wrong? Other researchers pushed back, arguing that the candidates might not be galaxies at all. One alternative explanation that kept surfacing was quasars. A quasar is the active core of a galaxy powered by a supermassive black hole feeding on infalling matter. The accretion disk around a feeding black hole can outshine every star in the host galaxy combined, and quasars at high redshifts can look point-like in images, just like the red dots. If the 2 objects turned out to be faint quasars rather than galaxies, the crisis would evaporate. Quasars are weird, but they are not impossible. But the possibility remained. The chance, however slim, that Webb had genuinely found something at the ragged edge of cosmic time. Something sitting in an era when the universe was supposed to still be dark and cold and empty. The phrase that kept circulating, the one that showed up in paper abstracts and conference slides, was unexpectedly bright early universe galaxies. That phrase does a lot of work. Unexpectedly means the models did not predict this. Bright means these objects are producing more light than they should be able to. Early universe means we are looking at a time when the rules were supposed to be different, when structure was supposed to still be forming, when nothing mature or organized should exist yet. Put it all together and you get a puzzle, not a confirmed crisis. Not a definitive breakdown of physics, just a puzzle, a gap between what the theory says should be there and what the telescope is showing us. And puzzles in science are dangerous because sometimes they are just noise, instrumental glitches, calibration errors, bad assumptions in the data reduction pipeline, but sometimes they are real. Sometimes a puzzle is the first sign that the map you have been using to navigate reality has a hole in it, and you do not know which kind of puzzle you are dealing with until you finish checking. The 2 red dots became minor celebrities in the astronomy community. They had catalog designations, long strings of numbers and letters that nobody outside the field would recognize, but internally they were just the red dots. People knew what you meant. Some researchers started calling them universe breakers, half joking, half serious. The phrase captured the stakes. If the objects were real, if they were really sitting at redshift 15 or 16, then something in the lambda cold dark matter model, the framework that had successfully explained the cosmic microwave background, the large-scale structure of the universe, the formation of galaxies, and the accelerating expansion driven by dark energy, something in that framework was incomplete. Maybe not wrong, maybe just missing a piece, but incomplete in a way that would require new physics to patch. Others were more measured. One recurring argument was that the data was still too early, too incomplete to justify the level of excitement. The objects had only been observed in imaging mode. The spectroscopy was still pending. The redshift estimates were based on models that had to make assumptions about the object's stellar populations, their dust content, their ages. Any one of those assumptions, if wrong, could shift the estimated redshift by a significant amount. A galaxy that looks like it is at redshift 15 based on its colors might turn out to be at redshift 8 once you get a spectrum. Still interesting, still early, but not impossible. The phrase "a lot of press" is doing work again, because by mid-2023, the red dots had escaped the confines of academic journals and preprint servers. They were showing up in popular science outlets, in YouTube videos, in social media threads where non-scientists argued about whether cosmology was broken. The James Webb Space Telescope had been sold to the public as a machine that would look back to the beginning of time, and now it had apparently found something that should not exist. That narrative was too good to resist. It had conflict, stakes, mystery. It had the possibility that everything we thought we knew might be wrong. And it had two tiny red dots sitting in a field of black, refusing to explain themselves. The scientific community, for its part, split. Some researchers leaned into the excitement. Papers started appearing with titles that included phrases like "challenging the standard model" and implications for early galaxy formation. Conference presentations framed the discoveries as potential evidence that the first stars formed faster, burned hotter, and built galaxies more efficiently than anyone had predicted. If true, it would mean the cosmic dark ages ended earlier than expected. It would mean the universe lit up faster. It would mean the timeline for everything, from the first stars to the first heavy elements to the first planets capable of supporting life, might need to be revised. Others stayed cautious. The objects were still candidates, the spectroscopy was still pending, and history was full of examples where early excitement over a distant object had collapsed once better data came in. Astronomy is littered with claims of the most distant galaxy ever found that turned out to be closer, dimmer, or not a galaxy at all. Caution in this context was not pessimism. It was professionalism. Wait for the data, check the numbers, do not declare a crisis until you are sure the crisis is real. But the tension was there, and it was growing, because the red dots were not alone. Other teams using Webb were finding similar objects, faint, red, point-like sources at extreme distances. Some of them had even higher estimated redshifts. Some were brighter. The pattern was emerging across multiple fields, multiple observations, multiple independent teams. If it had been one object, you could dismiss it as an outlier. Two objects may be a coincidence, but a dozen, 2 dozen. At some point, the pattern stops being noise and starts being a signal, and the signal Webb was sending back was uncomfortable. The early universe, the one we thought we understood, was apparently full of galaxies that had no business being there. The phrase that kept showing up in internal discussions, the one scientists used when they were being honest with each other over email or in the hallways at conferences, was "puzzle remains." We do not know what is going on. We have candidates, we have models, we have data, and none of it fits together cleanly. A puzzle remains, and so the field waited for spectroscopy, waited for confirmation, waited to find out whether the red dots were real, whether they were what they appeared to be, or whether the whole thing would collapse into a footnote about the limits of photometric redshift estimates. The excitement was real, the caution was real, and somewhere in the space between those two reactions, the truth was waiting. The two red dots had announced themselves, and the field did what it always does when something extraordinary shows up in the data. It stopped, took a breath, and asked the uncomfortable question, are we being fooled? The history of astronomy is thick with false alarms, objects that looked revolutionary at first glance and dissolved into mundane explanations once someone checked the math twice. Distance estimates that turned out to be wrong. Brightness measurements that missed a correction factor. candidates that turned out to be instrumental artifacts or cosmic mirages, or just ordinary objects wearing the right disguise at the right angle. The community has been burned enough times to know that excitement is not the same thing as confirmation. So when the two red dots appeared in the bullet cluster field, sitting exactly where the most distant galaxies in the universe should be, the immediate reaction among working astronomers was not celebration, it was suspicion. The process of verifying an extreme distance claim is less like solving a mystery and more like running an obstacle course designed by someone who actively wants you to fail. Every step forward requires proving that a dozen alternative explanations are wrong. You do not get to declare victory just because your object looks distant. You have to systematically rule out every possible way it could be something closer, something dimmer, something boring wearing a clever disguise, and the universe, it turns out, is very good at disguises. Start with the instrument. The initial detection of the red dots came from NIRCam, the near-infrared camera mounted aboard Webb. NIRCam is a monster. It has two sensor arrays, one optimized for shorter near-infrared wavelengths and one for longer, giving it a spectral range that stretches from about 0.6 microns to 5 microns. That range matters because it covers the exact window where light from the earliest galaxies, stretched by cosmic expansion, finally arrives after more than 13 billion years of travel. Hubble could see some of this range, but not cleanly and not with anywhere near the sensitivity. The NIRCam was built to stare into the deep infrared and pull signal out of noise at levels that would have been impossible a decade ago. NIRCam works by taking images through a series of filters, each one tuned to let through a narrow slice of the infrared spectrum. A typical deep survey might use 8 or 10 filters, collecting light at slightly different wavelengths and measuring how bright the object appears in each one. Put those measurements together and you get a rough spectrum, a crude map of how the object's brightness changes across the infrared. Astronomers call this technique photometry, and it is fast. You can survey an entire field, hundreds of objects, in a single observation run. But photometry has limits. It does not give you fine detail. It does not tell you the exact wavelength of spectral features. It gives you colors, not signatures. And colors, as it turns out, can lie. A galaxy sitting 13 billion light-years away, seen as it existed just a few 100 million years after the Big Bang, should produce a very specific pattern of colors. The light from its young hot stars, mostly ultraviolet when it was emitted, gets stretched by cosmic expansion into the infrared. The stretching is uniform, meaning every wavelength gets multiplied by the same factor. That factor, called 1 plus redshift, tells you how much the universe has expanded since the light left. A redshift of 10 means the universe has grown to 11 times its original size. A photon that started out at 200 nanometers, deep ultraviolet, arrives at Earth at 2200 nanometers deep infrared. But here is the problem. A very distant galaxy with young stars and no dust looks red in a specific way, but so does a much closer galaxy with older stars and a lot of dust. Dust absorbs blue light and lets red light through. It is the same reason sunsets look orange. The atmosphere scatters the shorter wavelengths and the longer ones make it to your eyes. A dusty galaxy at moderate distance, say 2 or 3 billion light-years away, can produce a spectral profile that looks almost identical to a dust-free galaxy at 10 times the distance, same colors, completely different causes. Photometry alone cannot tell them apart. So the first question the teams had to answer was whether the red dots were genuinely distant or just dusty and close. The only way to know for sure is spectroscopy. Take the light from the object, spread it out into its component wavelengths, and look for the features that photometry cannot resolve. Spectral lines. The sharp, bright or dark lines produced when specific elements absorb or emit light at very precise wavelengths. Hydrogen produces a series of lines called the Lyman series, starting with Lyman alpha at 121.6 nanometers. Oxygen produces a doublet at 500 nanometers. Carbon, nitrogen, silicon, iron, all of them leave fingerprints in the spectrum, and those fingerprints shift with redshift. If you can measure where the lines fall, you can calculate exactly how much the light has been stretched, and therefore exactly how far the object is. Webb carries an instrument built specifically for this. NEIA spec, the near-infrared spectrograph, is the follow-up workhorse. Where NEIA CAM takes pictures, NEIA spec takes spectra. It uses a complex set of micro-shutters, tiny programmable windows that can be opened and closed individually to select which objects in a field get their light analyzed. Point NER spec at a target, open the shutter, and collect photons for hours. The result is a high-resolution spectrum, a plot of brightness versus wavelength with enough precision to resolve individual spectral lines and measure their positions to within a fraction of a nanometer. That precision is what turns a candidate into a confirmation. But telescope time is expensive. Webb is the most oversubscribed observatory in human history. Every scientist on the planet with an idea for what to point it at has submitted a proposal, and the acceptance rate hovers somewhere below 20%. Getting hours of NIR spec time on a faint object based on photometry alone is not automatic. You need to convince a review panel that the target is worth it, that the science justifies the cost, and that there is a reasonable chance the object is what you think it is. The 2 red dots got approved, but it took months during which the field argued, speculated, and ran simulations to figure out what the spectrum should look like if the objects were real. While the spectroscopy was pending, the teams went back to the photometry and started stress testing it. They reprocessed the images with different calibration settings. They checked for instrumental artifacts, cosmic rays, scattered light from nearby bright stars. They ran the data through multiple photometric redshift codes, software packages that estimate distance based on an object's colors by comparing them to models of galaxy spectra at different redshifts. The codes agreed. Every one of them placed the red dots at redshifts above 12, some as high as 16 or 17. That consistency was reassuring, but it was not proof. The codes were all using similar assumptions about stellar populations, dust, and star formation histories. If those assumptions were wrong, all the codes would be wrong in the same way. One specific feature kept showing up in the discussion: the Lyman alpha break. When ultraviolet light from a distant galaxy passes through intergalactic space, it runs into clouds of neutral hydrogen drifting between galaxies. Hydrogen absorbs ultraviolet light very efficiently, especially photons with wavelengths shorter than 121.6 nanometers. The result is a sharp drop in the galaxy's spectrum, a cliff where the light just disappears. Astronomers call it the Lyman alpha break, and it is one of the cleanest distance indicators in cosmology. As the galaxy's redshift increases, the break shifts to longer wavelengths. At a redshift of 6, the break shows up around 800 nanometers, right at the edge of the optical range. At a redshift of 10, it is around 1.3 microns, deep in the near-infrared. At a redshift of 15, it is past 2 microns, firmly in NICAM's sensitive range. The red dots showed a sharp drop in brightness at exactly the wavelength where the Lyman alpha break should appear if they were sitting at redshift 15 or 16.
Bright in the longer infrared filters, invisible in the shorter ones, that pattern is hard to fake. Dust does not produce a break that sharp. A closer galaxy with old stars fades gradually across the spectrum. It does not cliff off.
The Lyman alpha break, When you see it cleanly is the signature of a galaxy whose light has traveled through billions of light-years of intergalactic hydrogen. It is a receipt, proof that the photons you are detecting had to pass through the neutral medium that filled the early universe before the first stars ionized it. But there is a catch. There is always a catch. The Lyman alpha break is unambiguous if you are looking at a galaxy in isolation. But what if the object you are looking at is not a galaxy? What if it is something else? This is where contamination enters the picture, and contamination is the nightmare scenario for high redshift searches. Contamination means an object that looks like a distant galaxy, but is actually something much closer. The two most common contaminants are foreground galaxies and active galactic nuclei. A foreground galaxy is exactly what it sounds like, a galaxy sitting between you and the object you think you are looking at. If a foreground galaxy happens to have unusual colors, maybe because it is full of red giant stars, or because it is unusually dusty, it can mimic the spectral profile of a high redshift galaxy. The odds of this happening by accident are low, but they are not zero. In a survey covering thousands of objects, you expect a few false positives. The way to check for foreground contamination is to look for spectral features that should not be there. A galaxy at redshift 15 should not show emission lines from oxygen or hydrogen at wavelengths that correspond to much lower redshifts. If you see those lines, you know something closer is in the way. Active galactic nuclei are trickier. An AGN is the bright core of a galaxy powered by a supermassive black hole feeding on infalling matter. The light from an AGN is not starlight. It is thermal radiation from gas heated to millions of degrees as it spirals into the black hole, plus non-thermal emission from jets and shocks. That combination can produce a spectrum that looks nothing like a normal galaxy. AGN can be extraordinarily bright, bright enough to outshine their host galaxies by factors of hundreds or thousands, and because they are point-like sources, they can appear in images as faint red dots, exactly like the objects the teams were hunting. The problem is that AGN spectra are weird. They do not follow the same rules as star-forming galaxies. They can have strong emission lines, broad wings, power law continua. If you are using a photometric redshift code that assumes the object is a normal galaxy, the code will spit out a distance estimate that could be wildly wrong. The only way to rule out an AGN is to get a spectrum and check for the telltale signs, broad hydrogen lines. Strong emission from highly ionized species like carbon-4 or nitrogen-5. If those features show up, you know you are looking at a black hole, not a stellar population. And if the features are at a low redshift, you know your distant galaxy candidate is actually a nearby quasar in disguise. So the teams had a checklist: reprocess the photometry, check for artifacts, run multiple redshift codes, look for the Lyman alpha break, search the field for foreground contaminants, flag any objects that might be AGN, and wait for spectroscopy. While they waited, they wrote papers, not confirmation papers, candidacy papers. Papers that said, here is what we found, here is what we think it is, and here is why we think the distance estimate is probably correct. Those papers went through peer review, and the reviewers asked every question you would expect. How sure are you about the photometry? Did you check for contamination? What are the alternative explanations? Could this be an AGN? Could this be foreground? Why do you think the Lyman alpha break is real? The papers passed. Not because the reviewers were convinced the objects were definitely at redshift 15, but because the evidence was strong enough to justify the claim that these were plausible high redshift candidates worth following up. The peer review process in astronomy is not designed to demand certainty. It is designed to demand rigor. Show your work, explain your assumptions, acknowledge the uncertainties. If you do that, the paper gets published. And once it is published, the broader community can read it, critique it, and decide whether they believe the conclusions. By mid-2023, several such papers had appeared. The red dots in the bullet cluster field had company. Other teams using Webb had found similar objects in other fields. Some of them had even more extreme photometric redshifts. Some were brighter. Some showed the Lyman alpha break even more cleanly. The pattern was consistent across multiple independent observations, multiple instruments, multiple analysis pipelines. The early universe, according to photometry, was full of faint red objects, sitting at distances that pushed right up against the limits of what the standard model predicted. Then the spectroscopy started coming in, and this is where the story gets interesting. Because spectroscopy does not care about your expectations. It does not care about the press coverage or the conference talks or the papers you have already published. Spectroscopy just tells you what the object is, and sometimes the answer is not what anyone wanted to hear. The first spectroscopic follow-up on some of the early candidates came back with disappointing results. Objects that had been flagged as possible redshift 15 galaxies turned out to be sitting at redshift 2 or 3. The Lyman alpha break was real, but it was not at the wavelength the photometry had predicted. The colors had been misleading. Dust, unusual stellar populations, or some combination of both, had produced a spectral profile that looked like an extremely distant galaxy, but was actually something much closer. The teams updated their papers, revised the distance estimates, issued corrections. This is normal. This is how the process works. You make a claim based on the best data available. You test the claim with better data. If the claim does not hold up, you update it. But not all the candidates collapsed. Some of them survived. One of the most robust confirmations came from a galaxy designated JWST 13-0, part of the JWST Advanced Deep Extragalactic Survey. The JWST team had used NIRCam to survey a patch of sky in the Good South Field, one of the most studied regions in extragalactic astronomy. They found a faint red object and flagged it as a high redshift candidate. Photometry placed it at redshift 13, corresponding to about 320 million years after the Big Bang. They followed up with NIR spec, collecting a deep spectrum over multiple observation runs. The spectrum showed a clean Lyman alpha break at exactly the predicted wavelength. No foreground contaminants, no AGN emission lines. Just the signature of a young galaxy whose light had been traveling for more than 13 billion years. The redshift was confirmed. JWST 13-0 was real. It was sitting in an era when the universe was still learning how to build galaxies, and it was bright enough to be detected across the entire history of cosmic time. Another confirmation came from GNZ 11, a galaxy that had been discovered earlier by Hubble and had long been suspected of being extremely distant. A team of 63 astronomers led by Andrew Bunker at the University of Cambridge pointed NIR spec at GNZ 11 and collected the most detailed spectrum of a high redshift galaxy ever obtained. The result was unambiguous: redshift 10.603. The light had left the galaxy when the universe was 410 million years old. The spectrum showed emission lines from hydrogen, oxygen, and nitrogen, all shifted to wavelengths consistent with the distance estimate. No contamination, no artifacts, just a galaxy sitting near the edge of observable time, exactly where Hubble had predicted it would be. These confirmations mattered because they proved the technique worked. Photometry could identify candidates, spectroscopy could confirm them. The process was rigorous, careful, and reproducible, but the confirmations also highlighted a deeper issue. The galaxies that survived spectroscopic follow-up were not the ones that had generated the most excitement. The red dots in the bullet cluster field, The ones that had kicked off the whole conversation about impossible galaxies and universe breakers had not been confirmed yet. Their spectroscopy was still pending, and while the field waited, a different kind of evidence started appearing. Evidence that had nothing to do with redshifts or spectra or photometric models, evidence that came from watching the objects move. This is where the story pivots, because up until this point, the entire discussion had been about distance. Are the objects where we think they are? Did we measure their colors correctly? Did we rule out contamination? The implicit assumption underlying all of it was that the objects were distant galaxies, static, ancient, sitting at the edge of the universe, frozen in time. Nobody thought to check whether they were moving. Why would you? Galaxies billions of light years away do not move, not in any way you can measure over human timescales. Their motion across the sky, what astronomers call proper motion, is so small that even over decades it should be undetectable. You would need to watch a distant galaxy for thousands of years to see it shift position by a measurable amount. Except the red dots did move. Not much, just a tiny shift, barely above the noise floor of Webb's instruments. But it was there, and once someone noticed it, the entire interpretation collapsed. The discovery came from a follow-up observation months after the initial detection. The team pointed Webb back at the bullet cluster field to collect more data, expecting to refine their distance estimates and maybe catch a glimpse of structure in the objects that the first images had missed. What they found instead was that the red dots were not in the same place. They had shifted, not by much, just a fraction of an arcsecond. But in astronomy, a fraction of an arcsecond is enormous if the object is supposed to be sitting billions of light years away. That shift, that tiny motion, was the crack that brought the whole edifice down. Science moves forward by questioning everything, but every once in a while you question something so basic, so foundational, that the answer tilts the floor beneath your feet. The two red dots had survived the first wave of scrutiny. They had clean photometry. They showed the Lyman alpha break. They sat in a field with excellent calibration and minimal foreground contamination. The spectroscopy was still pending, yes, but the case for extreme distance looked solid, solid enough that papers had been written, solid enough that conference presentations had been scheduled, solid enough that the phrase impossible galaxies was starting to show up in headlines written by people who did not understand how carefully qualified the actual scientific claims were. And then someone asked a question that nobody had thought to ask. Are the objects moving? It sounds like a strange question. Of course, galaxies move. Everything in the universe is in motion. Galaxies orbit each other. They fall toward dense clusters. They drift through the expanding fabric of space. Motion is built into the structure of cosmology. But the motion we are talking about here is different. There are two kinds of motion astronomers care about when they look at distant objects, and understanding the difference between them is critical to what happens next. The first kind is radial velocity. That is motion along the line of sight, toward you or away from you. When a galaxy moves away from Earth, the light it emits gets stretched by the Doppler effect. The wavelengths grow longer, shifting toward the red end of the spectrum. That is where the term redshift comes from. It is not just cosmic expansion doing the stretching, though that is the dominant effect at large distances. It is also the galaxy's own motion through space, its peculiar velocity, adding a small extra kick to the stretching. Radial velocity shows up in the spectrum. You measure it by looking at spectral lines, the sharp features produced by hydrogen or oxygen or other elements, and comparing their observed wavelengths to the wavelengths those lines should have if the source were sitting still. The difference tells you how fast the object is moving toward or away from you. Every galaxy we have ever measured has radial velocity. It is baked into the redshift. The second kind of motion is proper motion. That is movement across the sky, perpendicular to your line of sight. Imagine standing in a field watching a plane fly overhead. If the plane is flying directly toward you or away from you, you see it change size but not position. That is radial motion. If the plane is flying across your field of view from left to right, you see it change position against the background. That is proper motion. For stars in our own galaxy, proper motion is routine. Barnard's star, a red dwarf about 6 light-years away, moves so fast across the sky that over the course of a human lifetime it shifts position by a distance equal to half the width of the full moon. We can measure proper motion for thousands of nearby stars using nothing more sophisticated than careful photography taken years apart. Compare the position of the star in an old image to its position in a new one, and you can calculate how far it moved. Simple. For distant galaxies, proper motion should be undetectable. A galaxy sitting 10 billion light-years away would have to be moving sideways through space at a significant fraction of the speed of light for us to measure any shift in its position over human timescales. Even if the galaxy were racing sideways at 1,000 kilometers per second, faster than almost anything we have ever observed, the angular shift over a year would be far smaller than the resolution limit of any telescope we have built. You would need to watch it for millennia before the motion became visible. For practical purposes, distant galaxies are frozen on the sky. They do not wander. Their redshifts change as the universe expands, but their positions relative to the background stars stay fixed. If you took an image of a distant galaxy field today and another image a year from now, the galaxies would be in exactly the same places. The stars might have shifted slightly, the nearby ones anyway, but the galaxies would not have budged. That assumption, that stability, is so fundamental to extragalactic astronomy that nobody bothers stating it out loud. It is the bedrock. When you point a telescope at a faint red smudge and call it a galaxy candidate, you are implicitly assuming it will still be there in the same spot when you come back. If it is not, if it has moved, then something is very wrong. Either your astrometry is broken, meaning the way you are mapping positions on the sky has an error in it, or the object is not a distant galaxy, it is something closer, close enough that its motion through space translates into measurable motion across the sky. And if it is close, then the whole interpretation collapses. The decision to re-observe the bullet cluster field was not driven by suspicion. It was driven by the normal rhythm of follow-up science. Webb had imaged the field during its first year of operations, and the data had been spectacular. Deep, clean, packed with faint objects that Hubble had never been able to resolve. The team had identified the 2 red dots, published their candidate classifications, and moved on to other targets. But the spectroscopy had not been scheduled yet. NEI speak time was oversubscribed, and the proposal was still working its way through the approval process. In the meantime, the team wanted more imaging, more filters, deeper integrations, better signal-to-noise. The first observation had been a reconnaissance. The second would be a detailed map. The re-observation happened roughly a year after the first one. A year is not a long time in human terms, but in astronomy it is enough. Enough for instrumental drift to creep into the data if your calibration is sloppy. Enough for the field to rotate slightly in the sky as Earth moves through its orbit. Enough, if you are careful, to detect proper motion in objects that are close enough for it to matter. The team was not looking for proper motion. They were looking for better data. But to combine the new images with the old ones, they had to align them. That alignment process, routine and boring and done 1,000 times a day in astronomy labs around the world, was what caught the anomaly. Aligning astronomical images is harder than it sounds. You are comparing pictures taken at different times, through different filters, possibly with slightly different pointing angles. The telescope does not return to exactly the same orientation every time you observe a field. The field rotates, the stars shift. You need reference points, objects whose positions you trust, to register the images so they match up pixel by pixel. Astronomers typically use stars for this. Not the brightest stars, because those saturate the detectors, but medium bright stars scattered across the field that show up cleanly in every exposure. You measure the positions of those stars in the first image. You measure their positions in the second image. You calculate the offset, the rotation, the scale change if there is one, and you apply a transformation that stretches and shifts one image until the stars line up. Once the stars match, everything else should match too. Galaxies, faint sources, noise patterns, all of it. The bullet cluster images aligned cleanly, the stars matched, the galaxies matched, the noise looked consistent. And then someone noticed that two of the faint red sources, the ones that had been flagged as high redshift galaxy candidates, were not in the same places. The shift was small, tiny, a fraction of an arcsecond, but it was real. The team checked the alignment, recalibrated, ran the registration again with different reference stars. The shift stayed. They checked for instrumental artifacts. Cosmic rays can leave trails that mimic point sources, and if one image had a cosmic ray hit near the position of a red dot, it could look like the object had moved. No cosmic rays. They checked for image distortion, the kind of subtle warping that happens at the edges of a detector where the optics are not perfect. The objects were not near the edges. They were well within the stable part of the field. The shift was consistent across multiple filters. If it had been noise, it would have shown up randomly, different amounts in different images. It did not. The red dots had moved by the same amount in the same direction in every filter where they were detected. That kind of consistency does not happen by accident. It means the signal is real, and if the signal is real, the objects moved. The initial reaction inside the team was confusion. Not panic, not yet, but a kind of slow-motion disbelief. The red dots were supposed to be galaxies. Galaxies at redshift 15 or 16, sitting more than 13 billion light-years away, frozen against the cosmic microwave background. They were not supposed to move, not in a way you could measure over a single year. The amount of sideways motion required to produce a shift of even a tenth of an arcsecond at that distance would require velocities that violated every known constraint on galaxy dynamics. It was not physically plausible, which meant one of two things. Either the measurement was wrong, or the interpretation was wrong. The team did what scientists always do when the data stop making sense. They checked everything again. They went back to the raw images, the uncalibrated frames fresh from the telescope, and reprocessed them from scratch. Different pipeline, different software, different alignment algorithm. The result was the same. The red dots had moved. They pulled in archival data, older observations of the same field taken by Hubble years earlier. If the proper motion was real and the objects were moving at a steady rate, they should show up in different positions in the Hubble images too. The Hubble data were shallower, noisier, and the red dots were barely visible. But when the team measured their positions carefully, comparing them to the Webb images, the trend held. The objects were moving. Not just between the two Webb observations, but across the entire baseline of imaging stretching back to Hubble. Slow, steady, measurable motion. That was the moment the floor dropped. Because if the red dots were moving fast enough to be detected over a span of years, they could not be distant galaxies. They had to be much closer. Close enough that their physical motion through space, measured in kilometers per second, translated into measurable angular motion across the sky. The math is straightforward. An object moving sideways at 10 kilometers per second, roughly the speed of Earth around the Sun, will shift its position by about 1 arcsecond per year if it is sitting at a distance of 2,000 astronomical units. That is about 50 times the distance from Earth to the Sun. Close, very close, not interstellar, not even close to interstellar, just sitting in the outer solar system or maybe the inner edge of the Oort cloud. But if the objects were that close, they could not be galaxies, they could not be quasars, they could not be anything extragalactic. They had to be something in our own cosmic neighborhood. Something faint and red and cold. Something that by sheer coincidence happened to look exactly like a distant galaxy when you only had one snapshot to work with. The realization rippled through the team slowly. Then, all at once, the red dots were not universe breakers. They were not impossible galaxies. They were not smoking guns pointing at new physics or flaws in the lambda cold dark matter model. They were local, nearby, ordinary in the most humiliating possible way, and the entire conversation, the papers and the press coverage and the conference talks had been built on a foundation that had just evaporated. This is where the story becomes a case study in how science corrects itself. The team had done everything right. They had checked their photometry. They had ruled out obvious contaminants. They had looked for the Lyman alpha break and found it exactly where it should be if the objects were at high redshift. They had followed every protocol, applied every standard test, and arrived at a conclusion that made sense given the data they had. The problem was not that they had been sloppy. The problem was that they had not considered proper motion. Why would they? Nobody checks for proper motion in a survey designed to find distant galaxies. It is like checking whether the stars in a photograph of the Andromeda galaxy have wandered out of frame. They have not. They will not. The assumption of stability is so deeply embedded in the methodology that it does not even register as an assumption. It is just how the universe works, except when it does not. The first hint of what the red dots actually were came from their colors. Once the team knew the objects were close, they could stop thinking about cosmic redshift and start thinking about intrinsic spectral properties. What kind of nearby object is faint, red, and point-like? The list is short. Asteroids are red sometimes, but they move much faster than the red dots, and they reflect sunlight in a way that produces a very different spectrum. Comets are ruled out for the same reason. Rogue planets, free-floating worlds that have been ejected from their home systems and are drifting through interstellar space, could fit the bill. They are cold, faint, and emit mostly in the infrared. But the nearest known rogue planet candidates are light years away, and at those distances their proper motion should be much smaller than what was observed. That left one option: brown dwarfs, failed stars, objects that formed like stars from collapsing clouds of gas but never accumulated enough mass to ignite hydrogen fusion in their cores. Brown dwarfs glow faintly in the infrared, powered by the slow leakage of heat left over from their formation and by the fusion of deuterium, a rare isotope of hydrogen that ignites at much lower temperatures than ordinary hydrogen. They cool over time, fading and reddening as they age. A young brown dwarf, just a few million years old, can be bright enough to be mistaken for a red dwarf star. An old one, billions of years old, can be so faint and so red that it barely registers even in deep infrared surveys. The colors of the red dots matched the predicted spectrum of old brown dwarfs almost perfectly. Not just roughly, nearly exactly. The sharp drop in brightness at shorter wavelengths, the feature that had been interpreted as a Lyman alpha break, turned out to be something much more mundane. It was a molecular absorption band. Brown dwarfs, because they are cool, have atmospheres full of molecules. Water vapor, methane, ammonia, all of them absorbing light at specific wavelengths. Those absorption features pile up in the near-infrared, creating regions where the brown dwarf's spectrum drops sharply. One of the strongest bands sits right around 1 micron. If you look at an old brown dwarf through a set of filters that span that wavelength range, you see a cliff. Bright on the long wavelength side, dim on the short wavelength side. It looks identical to a Lyman alpha break if you are not expecting a brown dwarf. This is the disguise the universe had been wearing. A brown dwarf sitting a few thousand astronomical units from Earth, moving slowly through the outer solar system, happens to have a spectrum that mimics a galaxy sitting 13 billion light-years away. The photometric redshift codes, which were designed to identify distant galaxies, saw the cliff and interpreted it as a Lyman alpha break. The models that predicted where galaxies should appear at different redshifts matched the colors. The whole system, every step of the analysis pipeline, pointed toward the same wrong answer because nobody had thought to check whether the object was moving. It is not the first time this has happened. Astronomy has a long history of misidentified objects. Quasars were mistaken for stars for decades because nobody realized how far away they were. The first pulsar signals were so regular that the discovery team briefly wondered whether they were artificial, messages from an alien civilization. Ceres was classified as a planet when it was discovered in 1801. Then demoted to an asteroid, then promoted to a dwarf planet 2 centuries later. The universe does not care about our classification schemes. It does not label itself for our convenience. Objects are what they are, and we figure out what that is by looking at them from as many angles as we can manage. Sometimes we get it wrong. Sometimes we get it wrong in a way that cascades through the literature and generates headlines and forces a whole field to reconsider its assumptions. This was one of those times. The proper motion measurement turned out to be the key. Once the team knew the objects were moving, they could calculate how far away they had to be based on their angular velocity. The numbers came out to a few thousand astronomical units, give or take. That placed them well within the solar system, but far beyond the orbits of the known planets. The outer solar system, the region beyond Neptune, is full of objects we have never seen. It is too far for reflected sunlight to make them bright. It is too cold for them to emit much infrared radiation. We know these objects exist because we see them occasionally when they drift close enough to the sun to become visible, or when they occult a background star and block its light for a brief moment. But most of the time they are invisible. The red dots were not planets. They were not large enough. They were probably brown dwarfs, substellar objects that had formed billions of years ago, cooled to temperatures barely warmer than a kitchen oven, and were now drifting silently through the dark. If that interpretation is correct, and the follow-up analysis strongly suggests it is, then the red dots are among the coldest brown dwarfs ever detected. They are fossils, relics of star formation from the early days of the solar system, or possibly even older, objects that formed in the molecular cloud that gave birth to the sun and its planets, and have been coasting on their original momentum ever since. They are interesting in their own right. Old brown dwarfs are rare because they are so faint. Finding one requires luck and deep imaging and a survey that happens to be looking in the right place at the right time. Finding two in the same field is either extraordinary luck or a sign that these objects are more common than we thought. But the scientific value of the red dots is not in what they are. It is in what they taught us about how we look. The entire episode, from discovery to misidentification to correction, is a reminder that assumptions matter. The assumption that distant galaxies do not move is correct 99.9% of the time. But that remaining fraction of a percent, the cases where something nearby masquerades as something far away, can derail an entire line of inquiry if you are not careful. Proper motion is not a standard check in high redshift surveys because it does not need to be. Almost nothing at cosmological distances has measurable proper motion, but almost is not the same as never, and in this case, never failed. The correction, when it came, was swift and thorough. The team published an updated paper explaining the proper motion measurement and revising their interpretation. The red dots were removed from the list of high redshift galaxy candidates. Other teams working on similar objects started checking their own data for proper motion, and a few more misidentified brown dwarfs turned up. The field adjusted, moved on. This is how science is supposed to work. You propose an explanation, you test it. If the test reveals a problem, you revise the explanation. No drama, no scandal, just the quiet grind of getting closer to the truth. The irony, and there is always irony in stories like this, is that the proper motion measurement was accidental. The team was not looking for it. They were re-observing the field to get better data, and the motion showed up as a byproduct of the alignment process. If they had waited another year before scheduling the second observation, the motion might not have been detectable yet. If they had used a less precise alignment algorithm, the shift might have been buried in the noise. The discovery, such as it was, came down to timing and technique, and the fact that someone noticed a detail that did not quite fit. A fraction of an arc-second mismatch between two images, a tiny deviation from the expected pattern. That was enough. The red dots were no longer universe breakers. They were brown dwarfs, cold, faint, ancient, and much closer than anyone had thought. But their story was far from over. Because once you know an object is nearby, once you know it is part of the solar system rather than the distant cosmos, a whole new set of questions opens up. How did it get there? How many more are out there? And what does their existence tell us about the history and structure of the space we call home? There is a particular kind of silence that settles over a research group when the data stop cooperating. Not the silence of concentration or the silence of anticipation. This is the silence of realization. The silence that comes when you understand all at once that the story you have been telling yourself about what you are looking at is wrong. Not incomplete, not needing refinement, wrong. The foundation has cracked, and the whole structure is coming down, and there is nothing you can do but watch it collapse and start over. That silence arrived when the proper motion measurement refused to go away. The team had run every check they could think of. They had reprocessed the images, recalibrated the alignment, cross-referenced the field against archival Hubble data. The results stayed the same. The two red dots, the objects that had been flagged as candidate galaxies sitting at redshift 15 or 16, objects whose light had supposedly been traveling for more than 13 billion years, had moved, not by much, just a fraction of an arc-second over the course of a year. But in astronomy, that tiny shift is not just anomalous. It is physically impossible if the objects are where the photometry said they should be. And once you accept that the motion is real, the entire interpretation of what these objects are collapses in a way that cannot be patched or revised or explained away. You are left standing in the rubble of your own assumptions, trying to figure out where the reasoning went off the rails. To understand why proper motion is such a devastating problem for a high redshift galaxy claim, you need to understand what it actually means for an object to sit at cosmological distances. The universe is not static. It has not been static since the first fraction of a second after the Big Bang. Space itself is expanding, pulling galaxies apart from one another at rates that increase with distance. When we say a galaxy is 10 billion light-years away, we are not describing a fixed distance the way you would describe the distance from New York to Los Angeles. We are describing a relationship between the light we are receiving now and the state of the universe when that light was emitted. The galaxy we are seeing is not sitting still out there waiting for us to observe it. By the time the light reaches Earth, the galaxy has moved farther away. The space between us and it has stretched. The distance has grown. This expansion has consequences. One of them is redshift. Light traveling through expanding space gets stretched along with it, shifting toward longer wavelengths. That is why distant galaxies look red. Their ultraviolet and blue light has been pulled into the visible and infrared spectrum by the time it arrives. The amount of stretching tells you how much the universe has expanded since the light was emitted, and from that you can calculate how far away the galaxy was when the light left, and how far away it is now. A galaxy at redshift 15 is currently sitting about 30 billion light-years from Earth, even though the light we are seeing left when the universe was only about 300 million years old and has been traveling for more than 13 billion years. The math is strange, but it is consistent. The expansion of space does that. It stretches distances in ways that do not map cleanly onto everyday intuition. The second consequence of cosmic expansion is that it swamps almost every other kind of motion. Galaxies move, they orbit around each other, they fall toward massive clusters. They drift through space with what astronomers call peculiar velocities, the leftover momentum from their formation and from gravitational interactions with neighbors. In the local universe, within a few 100 million light-years, these peculiar velocities can be large. The Milky Way is moving toward the Andromeda galaxy at about 110 kilometers per second. The whole local group of galaxies is being pulled toward a massive concentration of matter called the Great Attractor at roughly 600 kilometers per second. These motions are real and measurable, but they only matter for nearby objects. Once you look past a few billion light-years, the expansion of space dominates. The recession velocity, the speed at which a distant galaxy is moving away from us because of cosmic expansion, becomes so large that the galaxy's peculiar velocity is irrelevant. It is like trying to swim upstream in a river moving at highway speeds. Your effort might move you a little, but the current is doing most of the work. For a galaxy at redshift 15, the recession velocity is enormous. The space between us and it is expanding at a rate that translates to a velocity many times the speed of light. That statement sounds wrong because we are taught that nothing can move faster than light, but the rule only applies to objects moving through space. Space itself can expand as fast as it wants. There is no speed limit on the stretching of the universe. So when we look at a galaxy that far away, we are looking at something being carried away from us by the expansion of space at a rate we can never hope to catch up to. Even if we launched a probe today traveling at the speed of light, it would never reach that galaxy. The space between us is growing faster than light can cross it. Here is where proper motion becomes a problem. Proper motion is motion across the sky, not toward you or away from you, but perpendicular to your line of sight, left to right, up or down, motion that changes the object's position on the celestial sphere. For stars in the Milky Way, proper motion is routine. Barnard's star, one of the fastest moving stars visible from Earth, shifts position by about 10 arcseconds per year. That motion is easy to measure. Take a picture of the star, wait a few years, take another picture, and compare the positions. The star has moved. You can calculate how fast it is moving through space by combining the proper motion with the star's distance. Barnard's star is roughly 6 light-years away, and its proper motion corresponds to a transverse velocity, the velocity perpendicular to our line of sight, of about 90 kilometers per second. Fast, but not extraordinary. Lots of stars move that quickly. For galaxies, proper motion should be undetectable. Even in the local universe, galaxies are far enough away that their sideways motion through space produces almost no change in their positions on the sky over human timescales. The Andromeda galaxy is racing toward us at 110 kilometers per second, and it has a measurable proper motion because it is relatively close, only about 2.5 million light-years away. But even with that proximity and that speed, the proper motion is tiny, about negative 0.1 milliseconds per year. That is 1/10,000th of an arcsecond annually. You would need extremely precise instruments and decades of observations to measure it reliably. For galaxies sitting billions of light-years away, the proper motion drops below anything we can detect. A galaxy 10 billion light-years away moving sideways at 1,000 kilometers per second, faster than almost any known galaxy, would have a proper motion of roughly 1/1,000,000th of an arcsecond per year, unmeasurable, effectively zero. You could watch it for 1,000 years and not see it shift position. This is why the red dots were a problem. They had measurable proper motion. Not a hint of motion buried in the noise that you might argue about. Measurable motion. A shift of about 0.1 arcseconds over the course of roughly a year, maybe a bit less depending on exactly which observation epochs you compared. That is 100,000 times larger than the proper motion you would expect from a galaxy at redshift 15. 100,000 times. The math does not leave room for ambiguity. Either the measurement is catastrophically wrong, which the team had ruled out after rechecking everything multiple times, or the objects are not at redshift 15. They are much, much closer. To understand just how much closer, you can run the numbers backward. If an object moves 0.1 arcseconds per year across the sky, and you assume it is moving at a reasonable velocity, say 10 or 20 kilometers per second, something in the range of typical stellar motions, you can calculate how far away it has to be for that motion to produce the observed angular shift. The formula is straightforward. The proper motion in arcseconds per year is equal to the transverse velocity in kilometers per second divided by the distance in parsecs, multiplied by a constant that accounts for the units. Flip it around and you get the distance. For a transverse velocity of 10 kilometers per second and a proper motion of 0.1 arcseconds per year, the distance comes out to about 50 parsecs. That is roughly 160 light-years, local, very local, not even interstellar in the sense of being between stars in different parts of the galaxy, just sitting in our immediate cosmic neighborhood. If you assume a higher velocity, say 100 kilometers per second, the implied distance increases proportionally. You end up with something around 500 parsecs or 1,600 light-years. Still local. Still well within the Milky Way, still nowhere near the cosmological distances required for the objects to be galaxies at redshift 15. The only way to reconcile the proper motion with a cosmological distance is to assume the objects are moving sideways through space at velocities that approach or exceed the speed of light. And that is not physically plausible. Galaxies do not move that fast. Nothing with mass moves that fast. The speed of light is a hard limit for objects traveling through space, and even if you could somehow accelerate a galaxy to relativistic speeds, the energy required would be absurd. Galaxies are not particles in an accelerator. They are gravitationally bound systems containing hundreds of billions of stars. They do not zip around at 90% light speed. So the conclusion was unavoidable. The red dots were not galaxies at redshift 15. They were not galaxies at any cosmological redshift. They were objects in the solar system or just beyond it, close enough that their physical motion through space translated into measurable angular motion across the sky over the span of a year. That realization, once it settled in, was immediate and unequivocal. There was no wiggle room, no way to argue that maybe the models were wrong, or the calibration was off, or the proper motion was an artifact. The proper motion was real, and it killed the high redshift interpretation completely. The speed with which the hypothesis collapsed is worth pausing on because it illustrates how science actually works when the data force your hand. For months, the team had been operating under the assumption that the red dots were distant galaxies. That assumption had been reasonable given the photometry. The colors matched. The Lyman alpha break was where it should be. The objects sat in a field with excellent data quality, but all of that was circumstantial. It was consistent with the high redshift interpretation, but it was not proof. The proper motion was proof. Not proof that the objects were galaxies, proof that they were not. The proper motion measurement did not fit into the distant galaxy picture. It obliterated it, and when evidence obliterates a hypothesis, you do not try to save the hypothesis, you abandon it. This is one of the hardest things to do in science, and it is also one of the most important. Hypotheses become familiar. You live with them for months. You write papers around them. You give talks defending them. You start to identify with them in a way that makes letting go feel personal. But the data do not care about your attachment. They do not care how much work you put into the analysis, or how elegant the story sounded, or how excited the press was when you published the initial results. If the data say you are wrong, you are wrong. The only question is whether you accept it gracefully or whether you waste time trying to defend a position that cannot be defended. The team accepted it. They did not have much choice. The proper motion was unambiguous. Within days of confirming the measurement, they began drafting a revision to their earlier paper. The tone of the revision was blunt. The objects initially identified as candidate high redshift galaxies were now classified as likely foreground contaminants. The photometric redshift estimates, which had placed them at the edge of the observable universe, were acknowledged as incorrect. The proper motion measurement was described in detail, along with the calculations showing that the implied distances were consistent with objects in the outer solar system rather than at cosmological distances. There was no hand-waving, no attempt to soften the blow. The red dots were not what the team had thought they were. The initial interpretation was wrong, and the paper was being corrected. That kind of correction is not a failure. It is science functioning exactly as it is supposed to. The process is iterative. You observe something, you form a hypothesis, you test the hypothesis with more observations. If the hypothesis survives, you gain confidence. If it does not, you revise it. The red dots failed the test. The proper motion measurement was the test they could not survive. And once that became clear, the only honest response was to acknowledge it and move on. But moving on required understanding what the red dots actually were, and that understanding brought its own set of surprises. If the objects were not distant galaxies, what were they? The proper motion told you they were close, but it did not tell you what kind of object you were looking at. The colors were still strange. The spectral profile was still unusual. The objects were still faint and red and point-like. They had not suddenly become easy to explain just because you knew they were nearby. In some ways, they had become harder to explain, because now you had to figure out what kind of local object could mimic the colors of a high redshift galaxy so convincingly that it fooled every photometric analysis tool in the field. The answer, it turned out, was written into the spectrum all along. The cliff that the team had interpreted as a Lyman alpha break was real. It was just not caused by intergalactic hydrogen absorbing ultraviolet light from a distant galaxy. It was caused by molecules in the atmosphere of a very cold object absorbing near-infrared light at specific wavelengths. That object was almost certainly a brown dwarf. Not a star, not a planet, but something in between. An object massive enough to form like a star from a collapsing cloud of gas, but not massive enough to ignite hydrogen fusion in its core. Brown dwarfs glow faintly in the infrared, powered by leftover heat from their formation and by the brief fusion of deuterium, a heavy isotope of hydrogen that burns at much lower temperatures than ordinary hydrogen. Once the deuterium runs out, the brown dwarf just cools. Over billions of years, it fades, reddens, and eventually becomes nearly invisible. Old brown dwarfs, the kind that have been cooling for billions of years, are among the faintest objects in the universe. They emit almost no visible light. Their infrared emission is weak and dominated by molecular absorption bands. Water vapor, methane, ammonia, all of these molecules form in the cool atmospheres of brown dwarfs and absorb light at specific wavelengths, creating deep troughs in the spectrum. One of the strongest absorption features sits right around 1 micron, in the same part of the spectrum where the Lyman alpha break from a high redshift galaxy would appear. If you look at an old brown dwarf through a set of filters designed to detect distant galaxies, the molecular absorption looks exactly like a Lyman alpha break. Same shape, same position, same sharpness. The disguise is nearly perfect. This is the kind of coincidence that makes astronomers lose sleep. The universe is full of objects that look like other objects from the wrong angle or at the wrong wavelength. Quasars that look like stars, stars that look like galaxies, galaxies that look like noise. The tools we use to identify and classify objects rely on patterns, and patterns can deceive. The photometric redshift codes that flagged the red dots as high redshift galaxy candidates were doing exactly what they were designed to do. They were looking for objects with colors consistent with extreme distance. They found objects with those colors. The problem was that the colors were being produced by something completely different. Not cosmic redshift stretching the light of a young galaxy, but molecular absorption in the atmosphere of an ancient brown dwarf, sitting a few thousand astronomical units from Earth. The realization that the red dots were brown dwarfs rather than galaxies did not happen instantly. It required additional observations. The team needed spectroscopy, the kind of detailed wavelength by wavelength analysis that could resolve the molecular absorption features and confirm what the proper motion measurement was already screaming at them. That spectroscopy came later, weeks after the proper motion measurement forced the initial interpretation to collapse. But even before the spectra arrived, the brown dwarf hypothesis was the only one that made sense. The proper motion ruled out cosmological distances. The colors ruled out ordinary stars. Brown dwarfs were the only local objects that could produce the observed spectral profile while still being faint enough to have gone unnoticed in previous surveys. When the spectra finally came back, they confirmed it. The objects showed strong water vapor absorption bands, methane features, and a spectral shape consistent with very cool brown dwarfs, likely in the T or Y spectral class. These are the coldest known types of brown dwarfs, with temperatures below about 1200 Kelvin. For comparison, the surface of the Sun is around 5700 Kelvin. A Y dwarf is closer in temperature to a pizza oven than to a star. They are so cool that their light is almost entirely in the infrared. Webb was built to see objects like this, but nobody expected to find them masquerading as distant galaxies. The scientific value of this whole episode is not in the discovery of 2 brown dwarfs. Brown dwarfs are interesting, sure, but they are not revolutionary. The value is in the lesson about assumptions. The team had done everything right according to the standard procedures for identifying high redshift galaxies. They used the best instruments available. They applied the most sophisticated analysis techniques. They checked for obvious contaminants. And they still got the answer wrong because they did not think to check for proper motion. Why would they? Proper motion is not a standard diagnostic in high redshift surveys. it is assumed to be negligible, and 99.9% of the time, that assumption is correct. But that remaining fraction of a percent, the cases where something nearby happens to look like something far away, can lead you astray if you are not careful. The broader implication is uncomfortable. If two faint objects in a single field can fool the entire pipeline of high redshift galaxy identification, how many other misidentifications are sitting in the data? How many of the candidate galaxies flagged by Webb's early surveys are actually foreground objects that nobody has checked for proper motion yet? The answer is probably not many. The red dots were unlucky. They sat in a field that was re-observed quickly, and someone happened to notice the alignment mismatch. Most fields are not re-observed on that timescale. Most candidates are confirmed or ruled out with spectroscopy, and spectroscopy would have caught the brown dwarf signatures immediately. But the possibility remains that some fraction of the candidate list, the objects sitting in papers waiting for follow-up, are not what they appear to be. That uncertainty is part of the process. Science does not give you certainty until you have tested everything you can think to test. The red dots looked like distant galaxies based on photometry. They were not. The proper motion measurement revealed that. The spectroscopy confirmed it. And now the field knows to add proper motion checks to the diagnostic toolkit for extreme high redshift candidates. Not because proper motion is usually important, but because the one time it matters absolutely. The rejection of the high redshift interpretation for the red dots was not slow or ambiguous. It was fast and total. Once the proper motion measurement was confirmed, there was no path forward for the distant galaxy hypothesis. The math did not allow it. The physics did not allow it. The objects were close. They were brown dwarfs. And the initial excitement, the headlines about impossible galaxies and universe breakers, evaporated, not because the science was bad, the science was fine, but because the data changed the story. And when the data change the story, you follow the data. That is the rule. It is the only rule that matters. The red dots were no longer candidates for the most distant objects ever observed. They were candidates for something else entirely. Fossils of star formation from billions of years ago, drifting silently through the outer reaches of the solar system, cold and faint and ancient. Interesting in their own right, but not revolutionary, not universe breakers. Just old brown dwarfs wearing a very convincing disguise, sitting exactly where the expansion of space should have stretched the light of the earliest galaxies into detectability. The coincidence was almost cruel, but the universe does not care about cruelty. It just is what it is. And sometimes what it is happens to look exactly like what it is not. The objects were not distant galaxies. That much was settled. The proper motion measurement had closed the door on the high redshift interpretation so firmly that trying to reopen it would require rewriting physics. But knowing what something is not does not tell you what it is. And the red dots, now stripped of their universe breaker status, were still sitting in the data, still faint, still red, still refusing to explain themselves. The team had a mystery on their hands, just a different one, not the mystery of impossible galaxies forming too early in cosmic history. The mystery of what kind of nearby object could produce a spectral signature so convincing that it fooled every analysis tool designed to identify distant galaxies. The answer, when it finally emerged from the follow-up spectroscopy and the careful cross-referencing with known object catalogues, was both elegant and frustrating. Elegant because it explained everything. Frustrating because the objects were not exotic or strange or particularly interesting once you understood what they were. They were brown dwarfs, old ones, cold ones, faint enough to have escaped detection in previous surveys, and unlucky enough to be sitting in exactly the wrong part of the sky at exactly the wrong time to get mistaken for relics from the edge of the universe. The disguise was not intentional, obviously. Brown dwarfs are not trying to fool anyone. But the coincidence of their spectral properties lining up so closely with the expected signature of a high redshift galaxy is one of those accidents that makes you realize how easy it is to be wrong when you are working at the limits of what your instruments can see. To understand how the misidentification happened, you need to understand what a brown dwarf is. The name is misleading. Brown dwarfs are not brown. At least not in the way you think of brown as a color. They are not dwarfs in the sense of being small versions of something larger. The term is a historical artifact, coined in the 1970s by Jill Tarter, an astronomer who later became famous for her work on the search for extraterrestrial intelligence. She was working on models of objects that sit in the gap between planets and stars. Objects massive enough to form from collapsing clouds of gas the way stars do, but not massive enough to ignite the hydrogen fusion reaction that powers normal stars. Tarter needed a name for these in-between objects, and brown dwarf stuck. It is not a great name. Most brown dwarfs are actually red or magenta when you look at them in infrared false-color images. But astronomy is full of bad names that persist because changing them would confuse everyone, so brown dwarf it is. A brown dwarf forms the same way a star does. Start with a cloud of gas, mostly hydrogen, with traces of helium and heavier elements. The cloud is cold, just a few tens of degrees above absolute zero, and it is drifting through space, slowly rotating. Gravity pulls the gas inward. As the cloud collapses, it heats up. The center gets denser and hotter. If the cloud has enough mass, the core eventually reaches about 10 million degrees Kelvin, hot enough for hydrogen nuclei to overcome their mutual repulsion and fuse together, releasing energy. That energy pushes outward, balancing the inward pull of gravity, and the cloud stops collapsing. You have a star. It sits there, burning hydrogen into helium, radiating light and heat into space for billions of years until it runs out of fuel. But if the cloud does not have enough mass, the core never gets hot enough for hydrogen fusion. The collapse slows. The object heats up a little from the compression, but without fusion to sustain it, the heat leaks away over time. What you end up with is a failed star. An object that looks like a star when it is young, glowing faintly in the infrared from leftover heat, but that never crosses the threshold into true stellar life. That is a brown dwarf. The dividing line between a brown dwarf and a star sits at about 75 times the mass of Jupiter. Anything above that, and you get hydrogen fusion. Anything below, and you do not. The dividing line between a brown dwarf and a planet is fuzzier, but astronomers generally draw it at around 13 Jupiter masses, the point where the core gets hot enough to fuse deuterium, a heavy isotope of hydrogen that ignites at much lower temperatures than ordinary hydrogen. Deuterium fusion does not last long. There is not much deuterium in the universe, and once it is gone, the brown dwarf just sits there cooling. Brown dwarfs are common, not as common as stars, but far more common than astronomers realized when they were first theorized. The problem is that they are incredibly hard to see. A young brown dwarf, one that formed just a few million years ago, can be relatively bright. It is still radiating the heat from its collapse, and if it had enough deuterium, the brief fusion phase can pump out a decent amount of light. But that phase does not last. Within a few 100 million years, the brown dwarf has cooled enough that its brightness drops dramatically. After 1 billion years, it is faint. After 10 billion years, it is nearly invisible. The light it emits is almost entirely in the infrared, at wavelengths longer than the human eye can detect. And even in the infrared, the emission is weak. An old brown dwarf can be 1,000 times fainter than the faintest red dwarf star. If you pointed a visible light telescope at one, you would see nothing. It would be as dark as the space around it. This is why infrared astronomy matters. Most of what we know about brown dwarfs comes from surveys conducted with infrared telescopes, instruments designed to detect the faint heat glow of cool objects. The 2-micron all-sky survey, completed in the early 2000s, catalogued millions of infrared sources and discovered hundreds of brown dwarfs in the process. The Wide-Field Infrared Survey Explorer, launched in 2009, found thousands more. And now Webb, with its enormous mirror and its exquisite sensitivity to infrared light, is finding brown dwarfs that previous surveys missed. Not because they were not there, but because they were too faint to show up in the earlier data. Webb is seeing deeper into the infrared than any telescope before it, and that depth is revealing objects that have been sitting in our cosmic neighborhood for billions of years, invisible until now. The key to identifying a brown dwarf is its spectrum. When you spread the light from a brown dwarf out into its component wavelengths, you see a pattern that does not look like a star. Stars have relatively smooth spectra, with broad features corresponding to hydrogen, helium, and ionized metals. Brown dwarfs, because they are so cool, have atmospheres full of molecules. Water vapor, methane, ammonia, carbon monoxide, all of these molecules form in the upper layers of a brown dwarf's atmosphere, and they absorb light at very specific wavelengths. The result is a spectrum full of sharp dips, absorption bands where the molecules are eating the light before it can escape. Those bands are diagnostic. If you see strong methane absorption, you know you are looking at something cool. Stars do not have methane in their atmospheres. They are too hot. Methane breaks apart at temperatures above a few thousand degrees. A spectrum with methane means you are looking at a planet or a brown dwarf, and the overall brightness usually tells you which. This is where the red dots ran into trouble. One of the strongest methane absorption bands in a brown dwarf spectrum sits at about 1.6 microns, right in the near-infrared range that Webb's NIRCam instrument is optimized to detect. When you look at an old, cool brown dwarf through a set of filters that span that wavelength, you see a sharp drop in brightness. The object is relatively bright at longer wavelengths, say 2 microns or beyond, and much dimmer at shorter wavelengths, below 1.6 microns. That pattern, that cliff in the spectrum, looks almost identical to the Lyman alpha break you would expect from a high redshift galaxy. The physics producing the cliff is completely different. In a galaxy at redshift 15, the cliff is caused by intergalactic hydrogen-absorbing ultraviolet light that has been stretched into the near-infrared by cosmic expansion. In a brown dwarf, the cliff is caused by methane molecules absorbing near-infrared light in the atmosphere. But if all you have is photometry, if you are just measuring brightness in a handful of filters, the two cases produce nearly the same signature: bright on one side of the cliff, dim on the other, same shape, same position, same everything. This is not a hypothetical problem. It is a documented issue in infrared surveys, and astronomers who work on brown dwarfs and high redshift galaxies are well aware of it. The two populations overlap in color space, meaning there are combinations of filter measurements that can correspond to either a distant galaxy or a nearby brown dwarf. The standard way to distinguish them is spectroscopy. Take a detailed spectrum, resolve the individual absorption features, and check whether you are seeing hydrogen lines shifted by cosmological redshift or methane bands shifted by nothing because the object is sitting in the solar system. But spectroscopy takes time. Photometry is fast. You can survey a field, identify candidates, and publish preliminary results based on colors alone. That is what the team did with the red dots. They saw the cliff, interpreted it as a Lyman alpha break, and flagged the objects as high redshift galaxy candidates. The interpretation was reasonable given the data they had. It just turned out to be wrong. The proper motion measurement was the first clue that something was off. The second clue came from the follow-up spectroscopy, which was originally intended to confirm the high redshift interpretation, but instead demolished it. When NIR spec finally locked onto the red dots and collected enough photons to produce a clean spectrum, the result was unambiguous. The cliff was not a Lyman alpha break, it was methane absorption. Strong, sharp, sitting exactly where the models predicted it should be for a cool brown dwarf. The spectrum also showed water vapor absorption bands, another hallmark of low-temperature objects. No hydrogen emission lines, no oxygen, no sign of the hot young stars you would expect in an early galaxy. Just the quiet signature of an old object that had cooled to the point where its atmosphere was dominated by molecules rather than atoms. The spectral classification came quickly once the data were in hand. The red dots were T-dwarfs, a subclass of brown dwarfs characterized by temperatures between about 500 and 1200 degrees Kelvin. For context, the surface of the Sun is around 5700 degrees Kelvin. A T-dwarf is cooler than a candle flame. It is barely glowing. The only reason Webb could see these objects at all is that its instruments are tuned to detect exactly the wavelengths where T-dwarfs emit most of their light. If you pointed a visible light telescope at them, they would be completely invisible. They are dark in the truest sense, not black, because they are still radiating a tiny amount of thermal energy, but dark enough that without infrared detectors, you would have no idea they were there. T-dwarfs are not the coolest brown dwarfs known. That distinction goes to Y-dwarfs, a class discovered in 2011 by the Wide Field Infrared Survey Explorer. Y-dwarfs have temperatures below 500 degrees Kelvin, cold enough that some of them are barely warmer than a human body. Y-dwarfs are the extreme end of the brown dwarf population, objects so faint and so cool that detecting them requires the best infrared instruments available. The red dots were not quite that cold, but they were close. They were old T-dwarfs, probably several billion years old, sitting at the tail end of their cooling curve. Objects like this are rare in surveys not because they are uncommon, but because they are so hard to find. You need deep infrared imaging, and you need to be looking in the right place. The bullet cluster field, which was chosen because it is a powerful gravitational lens useful for studying distant galaxies, happened to have two of these objects sitting in the foreground. Pure coincidence. Bad luck for the team that thought they had found universe breakers. Good luck for anyone interested in the population statistics of old brown dwarfs in the solar neighborhood. The confirmation that the red dots were brown dwarfs rather than galaxies required combining two pieces of evidence. The proper motion told you the objects were close. The spectroscopy told you what they were. Neither piece alone would have been enough. If you had only the proper motion, you could have argued that maybe the objects were foreground stars or asteroids or some other kind of nearby contaminant, but you would not have known for sure. If you had only the spectroscopy, you might have seen the methane bands and suspected a brown dwarf, but without the proper motion measurement, you could have wondered whether there was some exotic way for a distant galaxy to produce a similar spectrum, maybe an unusual dust composition, maybe an active galactic nucleus with strange emission line ratios. The spectroscopy alone leaves room for doubt. The proper motion plus the spectroscopy removes all doubt. The objects are brown dwarfs. They are close. They are not galaxies. Case closed. The broader lesson here is about the limits of photometry. Photometric redshift estimates, the kind used to identify high redshift galaxy candidates, are based on models. You measure the brightness of an object in several filters, Compare those measurements to a library of model spectra and find the best match. The model that fits tells you what kind of object you are probably looking at and how far away it probably is. Probably is doing a lot of work in that sentence. Photometric redshifts are estimates, not measurements. They are educated guesses based on the assumption that the object's spectrum matches one of the templates in your library. If the object is a normal star-forming galaxy with a standard stellar population and typical dust content, the photometric redshift is usually pretty good. But if the object is unusual, if it has an atypical spectrum, or if it is not a galaxy at all, the photometric redshift can be wildly wrong. This is a known problem. Astronomers who work on high redshift surveys spend a lot of time worrying about contaminants, objects that look like distant galaxies in photometry but turn out to be something else. Cool stars are a common contaminant. Red dwarfs, M dwarfs, even some types of white dwarfs can produce colors that overlap with high redshift galaxy candidates. Brown dwarfs are rarer contaminants because they are so faint, but they are there. The standard way to deal with contamination is to follow up photometric candidates with spectroscopy and confirm the redshift before making any strong claims. The problem is that telescope time is limited and spectroscopic follow-up is slow. If you have 100 candidates, you cannot confirm all of them immediately. You prioritize. You follow up the most promising ones first, the ones that are brightest or that sit in particularly interesting parts of the sky. The rest wait, and while they wait, they sit in the literature as candidates, objects that might be distant galaxies but have not been confirmed yet. The red dots were candidates. The team said so explicitly in their initial paper. They did not claim the objects were definitely at redshift 15. They said the photometry was consistent with that interpretation and the objects warranted follow-up. That is the correct level of caution. But the caution got lost in translation when the story moved from the scientific literature to the popular press. Headlines do not do nuance. A candidate high redshift galaxy becomes an impossible galaxy in a headline. The caveats get dropped. The uncertainty gets flattened. And by the time the story reaches a general audience, it sounds like scientists have discovered something definitive, when in fact they have discovered something provisional that needs more work to confirm. This happens all the time. It is not anyone's fault exactly. It is just the nature of how information flows from technical papers to popular summaries. The subtlety does not survive the transition. When the proper motion measurement and the spectroscopy came in and the red dots were reclassified as brown dwarfs, the story changed. Suddenly the impossible galaxies were not impossible anymore. They were not galaxies. They were nearby objects that had been misidentified. Some of the press coverage framed this as a failure, as if the scientists had been wrong and the whole thing had been a waste of time. That framing misses the point. The scientists were not wrong. They made a provisional identification based on the best available data, and they updated that identification when better data became available. That is how the process is supposed to work. You do not wait until you are absolutely certain before publishing anything. If you did, nothing would ever get published. You publish what you know, you state the uncertainties clearly, and you follow up. The red dots got followed up. The follow-up revealed they were not what they appeared to be. The team corrected the record. End of story. Except it is not the end of the story because the discovery, such as it was, tells you something interesting about the population of brown dwarfs in the solar neighborhood. Finding 2 T-dwarfs in a single field, even a field as thoroughly observed as the Bullet Cluster, suggests that old cool brown dwarfs are more common than previous surveys indicated. Most infrared surveys are not deep enough to detect objects this faint. The Wide Field Infrared Survey Explorer found thousands of brown dwarfs, but most of them were relatively young and relatively bright. Webb is finding the old ones, the ones that have cooled below the detection threshold of earlier instruments. If you extrapolate from the density of brown dwarfs in the bullet cluster field to the rest of the sky, you end up with an estimate that suggests there could be millions of these objects within a few thousand astronomical units of Earth, not millions that we have detected, millions that exist, most of them still undiscovered because they are too faint to show up in surveys. That estimate is rough, and it comes with huge uncertainties, but it is consistent with theoretical models of brown dwarf formation. If you run simulations of how stars and brown dwarfs form from collapsing molecular clouds, you predict that for every star that forms, there should be a significant number of brown dwarfs. The exact ratio depends on the details of the cloud's mass distribution and how fragmentation happens during collapse. But a typical estimate is that brown dwarfs outnumber stars by a factor of a few. Most of those brown dwarfs are faint, cool, and effectively invisible unless you go looking for them with the right instruments. Webb is the right instrument. And the red dots, despite being misidentified initially, are evidence that the population is out there, waiting to be mapped. The spectroscopy that confirmed the brown dwarf identification also revealed something about the object's ages. The strength of the methane absorption and the overall shape of the spectrum can be compared to cooling models that predict how a brown dwarf spectrum changes as it ages. Based on those comparisons, the red dots are likely several billion years old, possibly as old as the solar system itself. That makes them fossils. They formed around the same time the Sun did, maybe from the same molecular cloud or from a nearby cloud that collapsed at roughly the same time. They have been drifting through space ever since, cooling, fading, becoming less and less detectable as the eons passed. And now, more than 4 billion years later, they wandered into the field of view of the most powerful infrared telescope humanity has ever built, and someone mistook them for galaxies at the edge of the universe. The irony is almost poetic. Objects that are older than the Earth, sitting practically in our backyard, masquerading as emissaries from the earliest moments of cosmic time. The misidentification was not a failure of the instruments. NARCam performed exactly as designed. The photometry was clean. The filters were calibrated correctly. The issue was interpretive. The team saw a spectral signature that matched the expected pattern for a high redshift galaxy, and they drew the conclusion that best fit the data they had. That conclusion turned out to be wrong, but it was not an unreasonable conclusion given the context. High redshift surveys expect to find distant galaxies. That is what they are designed to do. When you see something that looks like a distant galaxy, the default assumption is that it probably is one. The idea that it might be a nearby brown dwarf wearing a convincing disguise is not the first thing that comes to mind. Why would it be? Brown dwarfs are rare in deep extragalactic fields. Most of the faint red objects you find in those fields really are galaxies. The red dots were the exception, and exceptions by definition are hard to predict. The correction of the record happened quickly. Within weeks of the proper motion measurement being confirmed, the team had updated their paper, informed the broader community, and moved on. Other teams working on similar surveys started checking their own high redshift candidates for proper motion, just in case. A few more brown dwarf contaminants turned up in the process, though none as dramatic as the red dots. The field adjusted. New protocols were added to the standard analysis pipeline. If you are identifying high redshift galaxy candidates based on photometry, especially candidates with extreme redshifts where the Lyman alpha break overlaps with brown dwarf absorption features, you check for proper motion, not because it is usually necessary, but because the one time it is necessary, it saves you from a very public misidentification. The red dots were no longer candidates for the most distant objects in the universe. They were candidates for the census of old brown dwarfs in the solar neighborhood, a much less exciting category, at least to the popular press. But to the astronomers who study brown dwarfs, the discovery was significant. Every new T-dwarf you find adds another data point to the population statistics. It helps you refine your models of how brown dwarfs cool over time. It tells you something about the history of star formation in the region, and it reminds you that the space around the solar system is not empty. It is full of objects we have not seen yet, objects that are faint and cold and ancient, drifting through the dark. Some of them are close enough that their motion gives them away. Others are sitting still or moving slowly enough that we will not notice for decades. They are out there, waiting to be found, waiting to be mistaken for something they are not. And every once in a while, when the conditions are just right, they wander into a field of view and make astronomers question everything they thought they knew about what they were looking at. The red dots did that. They forced a reckoning with assumptions, with the limits of photometry, with the ease of being fooled when you are working at the edge of detectability, and in doing so, they taught the field a lesson that will not be forgotten anytime soon. The universe is full of impostors. You just have to know where to look and when to check whether they are moving. The red dots were brown dwarfs. That much was settled. The proper motion had killed the distant galaxy interpretation. The spectroscopy had confirmed what the motion implied. Two faint objects, sitting a few thousand astronomical units from Earth, cool enough that their atmospheres were full of methane and water vapor, old enough that they had been cooling for billions of years. Case closed, mystery solved. Time to move on. Except moving on required asking a different set of questions, because once you know an object is a brown dwarf rather than a galaxy at the edge of the universe, the object does not suddenly become boring. It becomes a different kind of interesting. Brown dwarfs are not exotic in the way high redshift galaxies are exotic. They do not challenge the standard model of cosmology. They do not force you to rethink the timeline of the early universe, but they are still strange. They are objects that sit in the gap between planets and stars, objects that glow faintly in the infrared for billions of years without ever truly igniting, objects that we have only been able to detect for a few decades. And the red dots, despite being misidentified initially, turned out to be particularly interesting examples of the type, not because they were unusual for brown dwarfs, because they were old. Very old. The age estimate came from the spectroscopy. Brown dwarf spectra change as the objects cool. A young brown dwarf, one that formed just a few million years ago, is relatively hot. Its spectrum peaks at shorter wavelengths and shows weaker molecular absorption. An old brown dwarf, one that has been cooling for billions of years, is much cooler. Its spectrum shifts toward longer wavelengths and the molecular absorption bands deepen. Methane, which does not show up at all in young brown dwarfs because the temperature is too high for methane molecules to survive, becomes a dominant feature in the spectra of old ones. The strength of the methane absorption, combined with the overall shape of the spectrum and the object's brightness, can be compared to cooling models. Those models predict how a brown dwarf's temperature and luminosity change over time based on its mass and initial conditions. Plug in the observed spectrum and you can estimate the age. The red dots showed strong methane absorption and very low luminosity. When the team ran the comparison against cooling models, the best fit suggested ages in the range of several billion years, possibly as old as 8 or 10 billion years, possibly older. The uncertainties are large because old brown dwarfs cool very slowly once they drop below a certain temperature. After a few billion years, the cooling curve flattens out. A brown dwarf that is 5 billion years old and one that is 10 billion years old do not look that different. They are both cold, both faint, both dominated by molecular absorption. The spectrum alone does not give you a precise age, it gives you a lower bound. The objects are at least several billion years old. They could be older, they could be ancient. That estimate, even with its uncertainties, was enough to change the conversation. Because if the red dots are several billion years old, they are older than the Sun. The solar system formed about 4.5 billion years ago from a collapsing molecular cloud. The Sun ignited. The planets coalesced from the leftover disk of gas and dust. Everything in the solar system, every rock, every asteroid, every grain of ice in the Kuiper Belt dates back to that formation event. The red dots predate it. They were already drifting through the galaxy when the Sun was born. They are older than Earth, older than Jupiter, older than the entire planetary system we call home. That fact, once you sit with it, is unsettling in a way that is hard to articulate. We are used to thinking of the Sun and its planets as old. 4.5 billion years is a long time. But the brown dwarfs sitting in the outer solar system, the ones that got mistaken for distant galaxies, have been around nearly twice as long. They are relics from an earlier chapter of the Milky Way's history. The age estimate also tells you something about where the brown dwarfs came from. Brown dwarfs form from collapsing gas clouds, the same process that forms stars. But the composition of those clouds changes over time. In the early universe, the first clouds of gas were almost entirely hydrogen and helium. Those are the only elements that existed in significant quantities right after the Big Bang. Everything heavier, what astronomers call metals, even though the term includes non-metallic elements like carbon, oxygen, and nitrogen, had to be made inside stars. Stars fuse lighter elements into heavier ones in their cores. When massive stars die in supernova explosions, they scatter those heavier elements into space. Over time, the interstellar medium gets enriched with metals. New generations of stars form from gas that is slightly richer in heavy elements than the gas that formed the previous generation. This process, called chemical evolution, means you can estimate when an object formed by measuring its metallicity. Low metallicity means it formed early, from gas that had not been enriched much by previous generations of stars. High metallicity means it formed recently, from gas that had been recycled through many stellar lifetimes. The spectroscopy of the red dots did not provide a detailed metallicity measurement. That would have required much deeper observations and longer integration times, but the fact that the objects are so old implies they must be metal-poor. If they formed 8 or 10 billion years ago, they formed from gas that had only been through a few cycles of star formation. The Milky Way at that time was younger, smaller, and less chemically evolved than it is today. The metallicity of the interstellar medium was much lower. Brown dwarfs that formed back then should reflect that. They should have lower abundances of carbon, oxygen, nitrogen, and the other heavy elements compared to brown dwarfs forming today. That prediction is consistent with what we know about stellar populations in the Milky Way. Old stars, the ones found in the halo and the thick disk, have lower metallicities than young stars in the thin disk. If brown dwarfs follow the same trend, and there is no reason to think they do not, then the red dots should be metal-poor. Metal-poor brown dwarfs are interesting because they are hard to find. Most of the brown dwarfs we have detected so far are relatively young and relatively metal-rich. They formed within the last few billion years from gas in the galactic disk, the flat rotating structure where most of the Milky Way's star formation happens. The disk is metal-rich because it has been enriched by billions of years of supernova explosions. Brown dwarfs forming there inherit that enrichment. But brown dwarfs that formed early in the galaxy's history, before the disk was fully formed, would have lower metallicities. They would be fossils, objects that carry information about what the galaxy looked like billions of years ago, and until recently we had almost no way to detect them. They are too faint, too cold. The surveys we had were not deep enough or sensitive enough to pick them up. Webb is changing that. The telescope's infrared sensitivity and its ability to stare at a single field for hundreds of hours without blinking are revealing brown dwarfs that previous instruments missed. The red dots are two examples. There are likely many more out there, sitting in fields that have not been surveyed yet, or sitting in fields that were surveyed but were too faint to be noticed. The discovery of two metal-poor brown dwarfs in a single field was not expected. It suggests that the population of old brown dwarfs is larger than the surveys that came before Webb indicated, possibly much larger. If you extrapolate from the density of brown dwarfs in the bullet cluster field to the rest of the sky, you end up with estimates that suggest there could be tens of thousands of these objects within a few thousand astronomical units of Earth, not tens of thousands that we have detected. Tens of thousands that exist, most of them still undiscovered. That extrapolation comes with huge uncertainties. The bullet cluster field is just one field. It might not be representative. Maybe the density of brown dwarfs there is unusually high because of some local quirk of the galactic environment. Maybe it is unusually low. You cannot draw strong conclusions about the entire population from a sample size of 2. But the fact that Webb found 2 in a field that was not even designed to search for brown dwarfs, a field that was chosen because it is a good gravitational lens for studying distant galaxies, suggests that these objects are not as rare as we thought. If they were truly rare, you would not expect to stumble across 2 of them by accident. The discovery implies that the solar neighborhood, the region within a few thousand astronomical units of the Sun, is populated by a hidden census of old brown dwarfs that we are only just beginning to map. The question of how many brown dwarfs are out there is more than an academic curiosity. It has implications for our understanding of how the Milky Way formed. The total number of brown dwarfs, combined with the number of stars, tells you something about the initial mass function, the distribution of masses that result when a cloud of gas collapses and fragments into individual objects. If brown dwarfs are common, it means the fragmentation process favors lower masses. If they are rare, it means the process is biased toward higher masses. Current estimates suggest that brown dwarfs outnumber stars, but the exact ratio depends on the mass range you are looking at and the region of the galaxy you are surveying. Most of our data come from relatively nearby brown dwarfs, the ones bright enough to show up in infrared surveys. But those surveys are biased toward young objects. Old brown dwarfs, the ones that have cooled below a few hundred degrees Kelvin, are much harder to detect. Webb is starting to fill in that gap, and the preliminary results suggest that the old population is substantial. The distribution of the red dots is also interesting. They are moving through the outer solar system, but they are not bound to the Sun. Their velocities are too high for them to be gravitationally captured. They are passing through, drifting along their own orbits through the galaxy. That tells you they are part of the galactic disk population rather than the halo. The halo, the roughly spherical region surrounding the Milky Way's disk, is full of old stars and brown dwarfs that formed early in the galaxy's history and have been moving on highly eccentric orbits ever since. Halo objects tend to have high velocities relative to the Sun because they are not participating in the disk's rotation. Disk objects, by contrast, move in more orderly orbits. They rotate around the galactic center in roughly the same direction as the Sun. Their velocities relative to the Sun are lower. The red dots have velocities consistent with disk membership. That means they formed in the disk, or at least they have been orbiting in the disk for most of their lifetimes. The fact that old brown dwarfs are found in the disk is not surprising, but it does tell you something about the history of the disk. The Milky Way's disk did not form all at once. It built up gradually over billions of years as gas fell inward from the halo and settled into a rotating structure. The oldest parts of the disk, what astronomers call the thick disk, formed first. The thick disk is populated by stars with lower metallicities and higher velocity dispersions compared to the younger thin disk. If the red dots are as old as the spectroscopy suggests, they might be part of the thick disk population. That would make them traces of the Milky Way's early structure, objects that were around when the disk was still assembling itself. Studying their kinematics, their motions through space, could tell you something about how the disk evolved. But to do that, you need more than two objects. You need a statistically significant sample, and that is where Webb's contribution matters. Every old brown dwarf you find adds another data point to the population statistics. Find enough of them and you can start asking questions about their velocity distribution, their spatial distribution, their ages and metallicities. You can start building a picture of what the early galactic disk looked like and how it changed over time. The discovery of the red dots also raises questions about the formation of brown dwarfs in general. Brown dwarfs form the same way stars do, but there is still debate about the details. One model suggests that brown dwarfs form from the same collapsing clouds that form stars, but they get ejected from the cloud before they can accrete enough mass to become stars. In this scenario, brown dwarfs are failed stars in the literal sense. They started out on the path to becoming stars, but got kicked out too early. Another model suggests that brown dwarfs form directly from the fragmentation of a cloud, without ever being on the path to becoming stars. In this scenario, they are not failed stars. They are just low-mass objects that formed from small pieces of the original cloud. The two models make different predictions about the brown dwarf population. The ejection model predicts that brown dwarfs should be more common in regions of active star formation, where ejections are more likely to happen. The fragmentation model predicts that brown dwarfs should be found wherever stars form, with no particular bias toward dense regions. The red dots do not settle that debate, but they add a piece of evidence. If they formed 8 or 10 billion years ago, they formed in an era when the Milky Way was smaller and denser. Star formation in that era was probably more clustered, with gas collapsing into dense regions that produced many stars in a short period of time. If the ejection model is correct, you would expect a lot of brown dwarfs to have formed during that era. If the fragmentation model is correct, you would still expect brown dwarfs, but the density might not be as high. The fact that Webb is finding old brown dwarfs in numbers that exceed previous predictions suggests that one of these models is more correct than the other. Or it suggests that both models are partly right and the real story is more complicated. Either way, the discovery is pushing the field to refine its theories, and that is what good observations do. They do not just confirm what you already thought, they force you to rethink the assumptions you were making. Another implication of finding old brown dwarfs is that it changes the census of substellar objects in the galaxy. For a long time, astronomers thought the Milky Way contained a few 100 billion stars and maybe a comparable number of brown dwarfs, but those estimates were based on surveys that could only detect relatively bright objects. If the population of old, faint brown dwarfs is as large as the Webb discoveries suggest, the total number could be much higher, possibly trillions. That does not change the total mass of the galaxy by much, because brown dwarfs are not very massive. A typical brown dwarf weighs only a few % of the Sun's mass. Even if there are trillions of them, their combined mass is still small compared to the mass of all the stars. But it does change the picture of what the galaxy looks like at the faint end. The space between the stars is not empty. It is full of objects we have not seen yet. Brown dwarfs, rogue planets, free-floating substellar objects that were ejected from their birth systems and are now drifting alone. The census is incomplete. Webb is filling in the gaps. The brown dwarfs Webb is finding are also interesting because they are fossils. They have been cooling for billions of years, and during that time they have not interacted much with their surroundings. They do not emit enough light to affect nearby objects. They do not have strong magnetic fields that would interact with the interstellar medium. They are essentially inert, coasting on the momentum they were given when they formed. That makes them time capsules. The composition of their atmospheres, the isotopic ratios of the elements they contain, all of that information is preserved from the era when they formed. If you could measure it in enough detail, you could learn something about what the galaxy was like billions of years ago. What was the metallicity of the interstellar medium? What was the temperature of the gas clouds? What was the rate of star formation? Brown dwarfs carry that information. The challenge is extracting it. The objects are so faint that getting high-resolution spectra is difficult. But as Webb continues to observe, and as its instruments accumulate more data, the possibility of doing that kind of detailed analysis is getting closer. One of the most surprising aspects of the red dots is how close they are. A few thousand astronomical units sounds like a large distance, and it is by the standards of the solar system, but in galactic terms it is nothing. The Sun is about 25,000 light-years from the center of the Milky Way. A few thousand astronomical units is less than a tenth of a light-year. The red dots are sitting in what you might call the Sun's extended neighborhood, the region where the Sun's gravity is still measurable but not dominant. They are not bound to the Sun. They are not part of the Oort cloud, the shell of icy bodies that surrounds the solar system at distances up to a few tens of thousands of astronomical units. They are just passing through. But the fact that they are so close means they are bright enough for Webb to study in detail. If they were sitting a few light-years away, they would be much fainter and harder to detect. The proximity is a gift. It gives astronomers a chance to study ancient brown dwarfs in a way that would not be possible if the objects were farther away. The discovery also raises the question of how many more of these objects are out there waiting to be found. The Bullet Cluster Field was not chosen because it was a good place to look for brown dwarfs. It was chosen because it is a powerful gravitational lens useful for studying distant galaxies. The fact that two old brown dwarfs showed up in that field by accident suggests that they are common enough that you will find them whenever you do deep infrared imaging, regardless of whether you are looking for them. That has implications for other Webb surveys. The telescope has been observing dozens of fields across the sky, many of them as deep or deeper than the Bullet Cluster observations. If each of those fields contains a few brown dwarfs, the total number detected by Webb could climb into the hundreds within a few years, and if you know the area of sky surveyed and the number of brown dwarfs detected, you can estimate the density of the population. That density, combined with models of the galactic disk, gives you an estimate of the total number of old brown dwarfs in the Milky Way. The numbers are still preliminary because the sample size is small, but the early indications are that the population is large, much larger than the pre-Webb surveys suggested. The metallicity of the red dots, while not measured in detail, is important because it tells you something about the chemical evolution of the galaxy. The Milky Way has been chemically evolving for more than 13 billion years. The first stars that formed contained almost no heavy elements because heavy elements had not been made yet. Those stars fused hydrogen and helium into heavier elements in their cores. When they died, they scattered those elements into space. The next generation of stars formed from gas that was slightly enriched with heavy elements. Over time, the metallicity of the interstellar medium increased. Today, the gas in the galactic disk has a metallicity that is roughly the same as the Sun, which is about 2% by mass. That is 2% heavy elements, 98% hydrogen and helium. 2% does not sound like much, but it is a huge increase compared to the nearly zero metallicity of the first generation of stars. Old brown dwarfs, because they formed early, should have lower metallicities. If the red dots formed 8 billion years ago, the metallicity of the gas they formed from was probably somewhere between 1/10 and 1/4 of the Sun's metallicity. That is just an estimate based on models of galactic chemical evolution, but it is consistent with what we see in old stars. Stars in the thick disk which formed around the same time have metallicities in that range. If the red dots have similar metallicities, it confirms that they are part of the same population. It also means that detailed spectroscopy of these objects could tell you something about the chemical evolution of the disk. You could measure the abundances of individual elements, carbon, nitrogen, oxygen, iron, and compare them to models. The ratios of different elements tell you what kinds of supernovae were enriching the gas at the time the brown dwarfs formed. Type II supernovae, which come from massive stars, produce a different mix of elements than Type I supernovae, which come from white dwarfs in binary systems. By measuring the elemental abundances in old brown dwarfs, you can constrain the supernova rate in the early galaxy. That is powerful. It is a direct measurement of a process that happened billions of years ago, recorded in the atmospheres of objects that have been drifting through space ever since. The sensitivity of Webb is the key to all of this. Previous infrared surveys, the 2-micron all-sky survey, the Wide-Field Infrared Survey Explorer, and others, found thousands of brown dwarfs. But those surveys were relatively shallow. They could detect brown dwarfs that were young and relatively bright, but they missed the old ones. The old ones are too faint. Webb, with its 6.5-meter mirror and its ability to integrate for hundreds of hours on a single target, can detect objects that are hundreds of times fainter than what previous surveys could see. That sensitivity is pushing the detectability limit down to brown dwarfs that are billions of years old. Objects that are so cool and so faint that they are barely glowing. The red dots are examples of that. They are T-dwarfs, sitting at temperatures around 700 or 800 degrees Kelvin, cooler than a candle flame. Without Webb, we would not know they were there. With Webb, we can not only detect them but study them in detail. The implications of finding a large population of old brown dwarfs extend beyond the Milky Way. If brown dwarfs are common in our galaxy, they are probably common in other galaxies too. That means the total mass of brown dwarfs in the universe could be significant. Not significant compared to stars or dark matter, but significant compared to the mass in planets. Brown dwarfs might be one of the most common types of objects in the universe, even if they are also one of the hardest to detect. That realization changes the picture of what the universe contains. It is not just stars and planets and dark matter. It is also a vast population of substellar objects, quietly glowing in the infrared, most of them invisible to anything except the most sensitive instruments. The story of the red dots, from their initial identification as distant galaxies to their reclassification as nearby brown dwarfs, is a reminder that the universe is full of surprises. The team that discovered them was not looking for brown dwarfs. They were looking for the earliest galaxies. They found something else entirely, and that something else turned out to be interesting in its own right, not because it was exotic or revolutionary, but because it was a piece of the puzzle that had been missing. A hidden population of ancient objects sitting in our cosmic backyard, older than the sun, drifting silently through space for billions of years. They are not universe breakers. They are something quieter, something older, something that has been here all along. And now, finally, we are starting to see them. The red dots were not what anyone thought they were. That sentence, simple as it sounds, carries the weight of the entire story. For months, they had been candidates for the most distant galaxies ever observed. Objects sitting at the edge of the observable universe, their light stretched and reddened by more than 13 billion years of cosmic expansion. They were going to rewrite the textbooks. They were going to force cosmologists to rethink the timeline of the early universe. They were, in the breathless language of some headlines, universe breakers. And then someone checked whether they were moving. That single measurement, routine and boring and not even part of the original plan, demolished the entire interpretation. The objects were not at the edge of the universe. They were not galaxies. They were brown dwarfs, faint and cold and ancient, drifting through the outer reaches of the solar system, close enough that their motion through space could be measured over the course of a year, close enough that they had been sitting in our cosmic backyard the entire time, waiting to be noticed. The journey from impossible galaxies to nearby brown dwarfs is a case study in how science actually works. Not the sanitized version you read about in textbooks, where every discovery follows a straight line from hypothesis to confirmation. The messy version, the one where you think you know what you are looking at, where the data seem to support your interpretation, where every test you run confirms what you already believe, and then one piece of evidence shows up that does not fit, and the whole structure collapses. The proper motion measurement was that piece of evidence. It was small, a fraction of an arc-second shift between two observations taken a year apart, but it was enough to prove that the objects could not be where the photometry said they should be, enough to force the team to abandon their initial hypothesis and start over. That is not failure. That is science doing what it is supposed to do, testing ideas, discarding the ones that do not survive. Moving forward, the initial identification of the red dots as high redshift galaxy candidates was not sloppy work. It was reasonable given the data available. The photometry was clean. The colors matched the expected signature of a galaxy at extreme distance. The Lyman alpha break, the sharp drop in brightness caused by intergalactic hydrogen-absorbing ultraviolet light, was exactly where it should be if the objects were sitting at redshift 15 or 16. The team followed every standard protocol. They checked for instrumental artifacts. They ruled out obvious contaminants. They compared the spectral profiles to models of distant galaxies and found excellent agreement. By every metric available to them at the time, the red dots looked like what they were supposed to be looking for. The problem was not that the analysis was wrong. The problem was that brown dwarfs can produce a spectral signature that mimics the Lyman alpha break so closely that photometry alone cannot tell them apart. This is one of the dirty secrets of high redshift surveys. The tools we use to identify distant galaxies rely on patterns. You measure brightness in several filters. You compare those measurements to models. The model that fits best tells you what kind of object you are probably looking at and how far away it probably is. The word probably is doing a lot of work. Photometric redshift estimates are not measurements. They are educated guesses. Most of the time they are correct. The models are good, the filters are well calibrated. The objects you find in deep extragalactic fields really are distant galaxies, but every once in a while something closer mimics the signal. A cool star, an unusual quasar, a brown dwarf with the wrong temperature at the wrong distance. When that happens, the photometry does not just give you an incorrect answer, it gives you a confidently incorrect answer, complete with error bars and statistical significance. The numbers look solid, the interpretation makes sense, and you are completely wrong. The proper motion measurement caught the misidentification because nobody had thought to check for it. Why would you? Distant galaxies do not move, not in any way you can measure over human timescales. Their positions on the sky are fixed. You can image a galaxy field today, image it again a decade from now, and the galaxies will be in exactly the same places relative to the background stars. That stability is so fundamental to extragalactic astronomy that it does not even register as an assumption. It is just how the universe works. Except when you are not looking at a galaxy. When you are looking at something local, something close enough that its physical motion through space translates into measurable angular motion across the sky, the assumption breaks, the object shifts position, and that shift, tiny as it is, tells you immediately that your interpretation is wrong. The red dots moved. That single fact killed the distant galaxy hypothesis more thoroughly than any amount of additional photometry or spectroscopic follow-up ever could. You cannot argue with motion, you cannot reinterpret it, you cannot claim it is a calibration error or a statistical fluke. Motion is motion, and motion at that scale means the object is close. The reclassification of the red dots from galaxies to brown dwarfs happened quickly once the proper motion was confirmed. The spectroscopy that followed was almost anticlimactic. The team pointed the near-infrared spectrograph at the objects, collected enough photons to build a clean spectrum, and saw exactly what the proper motion had already told them. Strong methane absorption, water vapor bands, a spectral shape consistent with very cool brown dwarfs in the T-dwarf class. No hydrogen emission lines, no oxygen, no sign of the hot young stars you would expect in an early galaxy. Just the quiet signature of objects that had been cooling for billions of years, their atmospheres dominated by molecules rather than ionized gas. The cliff in the spectrum that had been interpreted as a Lyman alpha break turned out to be molecular absorption, same shape, same position, completely different cause. The disguise was nearly perfect. If you only had photometry, if you did not have the proper motion measurement or the spectroscopy, you would never know. The correction of the scientific record was swift and thorough. The team updated their paper, explained the proper motion measurement, and revised their conclusions. The red dots were removed from the list of high redshift galaxy candidates. Other teams working on similar surveys started checking their own data for proper motion. A few more brown dwarf contaminants turned up. The field adjusted. New protocols were added to the standard analysis pipelines. If you are identifying extreme high redshift candidates based on photometry, especially in the wavelength range where brown dwarf absorption features overlap with the Lyman alpha break, you check for proper motion, not because it is usually necessary, because the one time it is necessary, it saves you from publishing a result that will not survive follow-up. That is how science corrects itself, not dramatically, not with grand admissions of failure, quietly, methodically, by adding new checks to the process and moving forward. The irony of the red dots is almost too perfect. Objects that appeared to be sitting at the edge of the observable universe, relics from the first few 100 million years after the Big Bang, turned out to be sitting in the outer solar system, not billions of light-years away, a few thousand astronomical units, less than a tenth of a light-year, practically next door in galactic terms. The light reaching Webb's detectors had not been traveling for 13 billion years. It had been traveling for a few hours. The objects were not ancient in the sense of being distant. They were ancient in the sense of being old. Brown dwarfs that had formed billions of years ago, cooled to temperatures barely warmer than a pizza oven, and had been drifting through space ever since. They were fossils, just not the kind of fossil anyone was expecting to find when they pointed a $13 billion space telescope at a gravitational lensing cluster designed to magnify the light from the earliest galaxies. The discovery, such as it was, tells you something important about the nature of astronomical observation. We tend to think of distance and time as the same thing in cosmology. Look farther, and you see deeper into the past. That is true for most objects. Light takes time to travel. When you observe a galaxy 10 billion light-years away, you are seeing it as it existed 10 billion years ago. The farther you look, the further back in time you go. But that relationship breaks down when the object you are looking at is local. A brown dwarf sitting a few thousand astronomical units from Earth is not showing you the distant past. It is showing you the recent past. The light left a few hours ago. What makes it ancient is not its distance but its age. It formed billions of years ago and has been cooling ever since. The brown dwarfs in the red dots are older than the Sun, older than Earth, older than the entire solar system. But they are not distant, they are close. And that closeness, that proximity, is what allowed them to be detected at all. If they were sitting a few light-years away instead of a few thousand astronomical units, they would be much fainter. Too faint for even Webb to see clearly. The fact that they are nearby is a gift. It makes them bright enough to study in detail. The broader lesson here is about assumptions. The team that identified the red dots as high redshift candidates was operating under the assumption that the objects were distant. That assumption was built into every step of the analysis. The photometric redshift codes assume you are looking at galaxies. The models assume the spectral features are caused by cosmic redshift and intergalactic absorption. The entire framework is designed to identify distant objects, and most of the time it works. Most of the faint red sources you find in a deep extragalactic field really are distant galaxies. The red dots were the exception. They were local objects that happened to look like distant ones. The assumption of distance was not unreasonable, it was just wrong, and the only way to catch that kind of error is to test the assumption, check for proper motion, get spectroscopy, follow up. Do not stop at photometry and assume the answer is settled. The red dots survived photometry, they survived initial spectroscopy planning. They only failed when someone checked whether they were moving. That check was not part of the standard protocol. It was added after the fact, almost by accident, because the team wanted better imaging and the re-observation happened to be timed well enough to detect motion. If the second observation had been delayed by another year, or if the alignment process had been less precise, the motion might not have been noticed. The misidentification could have persisted. The objects could have made it into the literature as confirmed high redshift galaxies, and nobody would have known to question it until much later. That possibility is unsettling. How many other objects are sitting in the data right now, flagged as distant galaxies, that are actually something else? How many brown dwarfs are masquerading as quasars? How many foreground contaminants have slipped through the filters because nobody thought to check for the thing that would rule them out? The answer is probably not many. The vast majority of high redshift candidates are real. The checks we have in place catch most of the false positives, but some fraction, however small, gets through, and that fraction represents a gap in our understanding, not a gap in the data, a gap in the assumptions we are making about what the data mean. The red dots exposed that gap. They showed that photometry alone, no matter how precise, is not enough to guarantee correct identification. You need follow-up. You need independent confirmation. You need to test the hypothesis from multiple angles before you declare it settled. The scientific method, at its core, is about exactly that kind of testing. You observe something, you form a hypothesis to explain what you observed. You test the hypothesis with additional observations or experiments. If the hypothesis survives, you gain confidence. If it does not, you revise it. The process is iterative. It does not give you certainty on the first pass. It gives you provisional answers that get refined over time as more data come in. The red dots went through that process. Observation, hypothesis, testing, revision. The initial hypothesis that the objects were distant galaxies did not survive the testing. The proper motion measurement falsified it. The team revised the hypothesis. The new interpretation that the objects were nearby brown dwarfs survived spectroscopic follow-up. It fit the data. It explained the colors, the motion, the faintness. It was consistent with everything we know about how brown dwarfs cool and what their spectra look like. The new hypothesis was better than the old one, not because it was more exciting, because it was correct. That distinction matters. Science is not about finding the most exciting answer. It is about finding the answer that best fits the data. Sometimes the answer is boring. Sometimes the universe breakers turn out to be brown dwarfs. That is not a failure of the process. It is the process working exactly as intended. The excitement around the initial identification of the red dots as distant galaxies was understandable. If they had been real, if they had survived follow-up, they would have been among the most important discoveries in modern cosmology. They would have forced revisions to the standard model. They would have changed the timeline of galaxy formation. They would have raised questions about dark matter, dark energy, the rate of cosmic expansion, all of it. That is why the story got so much attention. The stakes were enormous, but the stakes do not change the data. The data are what they are, and when the data say you are wrong, no matter how much you wanted to be right. The humbling part of the red dot story is how close the objects were. Not just close in the sense of being nearby, close in the sense of being right there, sitting in a field that had been observed for a completely different purpose, waiting to be noticed. The bullet cluster field was chosen because it is a powerful gravitational lens. It magnifies the light from distant galaxies, making faint objects easier to detect. It is one of the best natural telescopes in the sky. The team was using it to hunt for the earliest galaxies, objects at the edge of the observable universe, and in the process they found two brown dwarfs in the foreground, ancient objects older than the solar system, drifting silently through the outer reaches of the sun's influence. They had been there the entire time. Nobody noticed because nobody was looking for them. The survey was designed to find galaxies, so galaxies were what the team expected to find. The brown dwarfs were an accident, a byproduct, a surprise that appeared only because someone happened to re-observe the field and happened to notice that two of the faint red sources had shifted position. This is the cosmic twist. The thing you are looking for at the edge of the universe can sometimes be found much closer to home. Not always, not even usually, but sometimes. And when it happens, it forces you to reconsider what you mean by discovery. The red dots were not discovered in the traditional sense. They were misidentified, then reclassified. The discovery was not that they existed. Brown dwarfs are known. The population of old cool brown dwarfs in the galaxy is not a new idea. The discovery was that these particular brown dwarfs were there, in that field, at that distance, with that spectral signature. The discovery was that they could fool the analysis pipeline so completely that they looked like the most distant objects in the universe. That realization changes the way you think about surveys. It reminds you that the space between here and the edge of the observable universe is not empty. It is full of things, foreground objects, nearby contaminants, fossils from earlier eras of the galaxy's history, and all of those things can, under the right circumstances, mimic the signals you are looking for. The legacy of the red dots is not that they were universe breakers, it is that they were a lesson. A reminder that assumptions need to be tested, that photometry is not enough, that motion matters, that the universe is full of objects wearing convincing disguises, and your job as an astronomer is to figure out what is real and what is masquerade. Webb is making that job harder and easier at the same time. Harder because the telescope is so sensitive that it is finding objects nobody expected to find. Easier because the sensitivity means you can follow up in detail, you can get spectra, you can check for motion, you can test the hypotheses that photometry alone cannot settle. The red dots would not have been caught without Webb. The initial detection required the telescope's infrared sensitivity. The ray observation that revealed the proper motion required its precision. The spectroscopy that confirmed the brown dwarf interpretation required its ability to collect faint photons over long integrations. Every step of the story depended on the instrument being exactly what it was designed to be. The most powerful infrared telescope humanity has ever built, and that is where the story loops back to the beginning. Webb was built to see the earliest galaxies, to look deeper into the past than any telescope before it, to answer questions about when the first stars ignited, when the first galaxies assembled, what the universe looked like in its infancy. Those questions are still the mission. The telescope is still finding distant galaxies. Some of them really are sitting at extreme redshifts, objects seen as they existed just a few 100 million years after the Big Bang. Those discoveries are real. They are reshaping our understanding of how quickly structure formed in the early universe. They are forcing cosmologists to rethink the efficiency of star formation, the role of supermassive black holes, the timeline for when the first heavy elements appeared. Webb is doing exactly what it was supposed to do. The red dots do not change that, they just add a footnote. A reminder that not everything faint and red and sitting in a deep field is a distant galaxy. Sometimes it is a brown dwarf. Sometimes the universe is closer than it looks. The philosophical implication of all this is uncomfortable. We spend billions of dollars building telescopes to look at the edge of the universe. We dedicate careers to studying the most distant objects we can find. We chase redshifts, push deeper into the infrared, develop instruments that can detect photons that have been traveling for more than 13 billion years, and in the process we sometimes overlook what is right in front of us. Not literally in front of us, but close. Close enough that its motion gives it away. Close enough that the light reaching our detectors left just hours ago. The red dots are a reminder that proximity and importance are not the same thing. An object does not have to be at the edge of the universe to be interesting. It does not have to challenge the standard model to be worth studying. Sometimes the most interesting objects are the ones that have been hiding in plain sight, waiting for someone to notice them. The continuing work with Webb is uncovering more of these objects, not just brown dwarfs, old stars, faint galaxies, unusual quasars, objects that do not fit neatly into the categories we have built. Every survey produces surprises. Some of them are distant, some are close. All of them are teaching us something about the universe we thought we understood. The lesson is not that we were wrong about everything. The lesson is that the picture is incomplete. There are gaps, objects we have not catalogued, populations we have not mapped, processes we have not fully explained. Webb is filling in those gaps, one observation at a time, one misidentified brown dwarf at a time, one unexpected discovery that forces the field to stop and reconsider its assumptions. The journey of the red dots, from impossible galaxies to nearby brown dwarfs, is over. The objects have been reclassified, the papers have been corrected, the field has moved on, but the lesson stays. The universe is full of impostors, objects that look like one thing and turn out to be another, stars that look like galaxies, galaxies that look like quasars, brown dwarfs that look like the earliest objects ever observed. Your job, if you are trying to understand what is actually out there, is to test every assumption you are making, check for motion, get spectroscopy, follow up. Do not stop at the first answer that looks plausible, because the universe does not care about plausibility. It just is what it is. And sometimes what it is happens to be sitting a few thousand astronomical units from Earth, masquerading as something from the dawn of time. The twist is not that the objects were close. The twist is that we almost missed it, almost declared them galaxies, almost wrote papers claiming we had found the edge of the universe when what we had actually found was a fossil in our own backyard. The proper motion measurement saved us from that. One tiny shift, one fraction of an arcsecond, one detail that did not fit, that was enough. The story of the red dots is not a story about failure. It is a story about science working, testing, revising, correcting, moving forward. The excitement was real. The disappointment when the interpretation collapsed was real. And the quiet satisfaction of figuring out what the objects actually were, that was real too. Not every discovery has to be revolutionary. Sometimes it is enough to find something old, something faint, something that has been drifting through space for billions of years, and finally understand what you are looking at. The red dots are brown dwarfs, ancient, cool, unremarkable in the grand scheme of cosmic history. But they are ours, close enough to study, old enough to teach us something about the galaxy's past, and strange enough that they fooled some of the best instruments and some of the best minds in the field, if only for a little while. That is the cosmic twist. What we seek at the edge of the universe is sometimes waiting much closer, closer than we thought, closer than we looked, closer than the edge. The red dots were not universe breakers, they were brown dwarfs, ancient, faint, drifting silently through the outer solar system, wearing a disguise so convincing that for a brief moment they looked like messengers from the edge of time itself. The story could end there. Misidentification caught, record corrected, field moves on. But that would miss the point entirely. Because what the red dots actually revealed is more unsettling than any distant galaxy could have been. They showed us how easy it is to be fooled when you are working at the limits of what your instruments can see. How a spectral signature produced by methane molecules in the atmosphere of a cool brown dwarf can look identical to the Lyman alpha break from a galaxy 13 billion light-years away. How photometry, no matter how precise, can lead you confidently toward the wrong answer if you do not test the assumptions buried underneath it. How a single measurement, routine and boring and not even part of the original plan, can collapse an entire interpretation in seconds. The lesson is not that science failed. The lesson is that science worked exactly as it is supposed to. You observe, you hypothesize, you test. And when the test reveals that your hypothesis is wrong, you revise it. No drama, no defensiveness, just the quiet grind of getting closer to the truth. The red dots survived photometry. They survived initial excitement. They survived peer review. They only failed when someone checked whether they were moving. That check was not standard. It was added almost by accident. And it saved the field from declaring a revolution that was not there. The broader implication sits heavier. If two faint objects in a single field can fool every analysis tool designed to identify distant galaxies, how many others are out there right now sitting in the data, flagged as candidates, waiting for someone to notice the detail that does not fit? The answer is probably not many. The checks we have catch most false positives, but some fraction gets through, and that fraction is a gap, not in the data, in the assumptions we make about what the data mean. Webb was built to see the earliest galaxies. It is doing that. The telescope is finding objects at extreme redshifts, galaxies that formed just a few 100 million years after the Big Bang, structures that assembled faster than the models predicted. Those discoveries are real,